Good morning, good afternoon, everyone. Welcome to just a second. I would like to share my screen. Welcome to the third day of the first IAHR training course on modeling software for transient flows. It's been an exciting journey so far with insightful presentations and discussion on key challenges and cutting-edge approaches in transient flow modeling. Let's take a brief look at what we have covered over the past 2 days. On Monday, we started with a comprehensive overview of transient flow modeling by Mohamed Ghidawi. Then Anton's slides highlighted the complexities of modeling transient flows in large-scale hydraulic infrastructure. In the afternoon, Brian Carney and Brian Singh presented on how to handle the unique challenges of transient models. And then Anif Chaudhry introduced a powerful software tool, WH80 software for analyzing water hammer effects in pumping system and hydropower plants. Yesterday, we explored the application of 3D CFD simulations in transient flow processes with Yongguang Cheng, followed by Sam van de Zwam, who discussed Wanda, a powerful software tool for simulation of transient, and he analyzed in details different boundary conditions. And then we have had Christophe Nicolette demonstrated the transient analysis of hydropower systems using Simpson. And now, moving on to today's program, I will be sharing this session with Professor José Vasconcelos from Auburn University. We have an excellent lineup of speakers covering a range of advanced topics. We begin with Professor Kankan from Hawaii University, who will present his work on three-dimensional transient hydraulic behavior in pumped storage systems. This will be followed by Professor Enrique Cabrera from University of Valencia, who will introduce a Latin-free transient network analysis software, Allievi. And finally, Trey Walters from AFT Impulse will conclude the day with a session on surge transient modeling, including real-world case studies. Each session will be followed by a Q&A discussions, so I encourage you to use the Q&A box for your questions to our speakers. I Also would like to thank our sponsor, Deltares, Bentley, and Power Vision Engineering, and also our supporters, the China Society for Hydropower Engineering and the Italian Centro Studi Sistemi Idrici. It's a pleasure for me to introduce our first speaker, Professor Kan Kan, Associate Professor at Ohio University, China, and Director of its Research Institute of Pump Storage Technology. He holds a PhD in Water Conservancy and Hydropower Engineering and was a visiting PhD student at the University of Minnesota. His research focuses on hydraulic machinery for pump storage system with over 100 publications. Professor Kan has led national and industrial projects, received several prestigious awards, and was named among the world's top 2% scientists by Elsevier. He also developed a CFD-based method to improve transient processes in pump storage units that he will present today. And we are honored to have him with us. So welcome, Professor Kan. The screen is yours.
Okay. Thanks for Sylvia's introduction. Okay. Okay, ladies and gentlemen, good afternoon. I'm Kan Kan from Ohio University, China. I feel so excited to be here today to present our research on transient simulation technology for pumped storage units. The focus of my presentation is three-dimensional transient hydraulic behavior in pumped storage systems, an integrated simulation analysis and optimization framework. In this talk, I will introduce that how advanced high-precision simulation techniques can address the challenges associated with hydraulic instability during rapid operational transitions. In this presentation, I will systematically cover the research background, the simulation technologies we employed, the analytical methods used, engineering applications, and finally, the future prospects. Currently, the global energy landscape is rapid shifting towards renewable sources. Take China, for instance. By the end of 2024, the combined installed capacity of wind and solar power is expected to reach 1.41 billion kilowatts, accounting for 42% of the nation's total installed capacity. However, the inherent intermittency of wind and solar power presents a major challenge, with daily output fluctuation soaring as high as 80% of installed capacity. This poses substantial risks to grid frequency and stability. As a result, modern power systems are increasingly leaning on faster response regulation resources to maintain stability. Among the technologies available, pumped storage stands out as the only solution capable of providing gigawatt-scale capacity with response time quick as minutes and even seconds. As the stabilizer of modern power systems, pumped storage stands out as the most mature and cost-efficient solution for large-scale energy storage. Peaking shaving, frequency regulation, and phase adjustment. Its unmatched reliability and efficiency highlight its critical role in driving the global energy transition, making it an indispensable asset for sustainable energy future. Its core function can be summarized in three key areas. First, it balances peak and off-peak demand through daily regulation cycles. Second, it supports grid frequency regulation with precision down to the second. Third, it acts as an emergency backup power source, instantly filling load gaps during critical situations. These capabilities make it an important component in ensuring grid stability and reliability. This multi-dimensional regulatory capability makes pumped storage an essential safeguard against the stochastic fluctuations of wind and solar power. However, it also places considerable engineering demands on controlling the transition processes during frequent operational mode shifts, an issue that lies at the core of our research efforts. Okay, traditional research methods, while invaluable, have inherent limitations. Model testing often suffers from scale effects, leading to poor hydraulic similarity. Full-scale prototype testing, on the other hand, offers limited operational coverage and risk in reversible equipment damage. Additionally, one-dimensional simulations, such as the method of characteristic, the MOC method, are effective in capturing transient phenomena in long pipelines, but fall short in resolving the complex three-dimensional internal flow within the pumped storage unit. These gaps highlight the need for more advanced approaches to fully understand and optimize system performance. To overcome these challenges, we have developed a full-scale three-dimensional transient simulation framework that achieves a threefold breakthrough in realism, accuracy, and precision. Realism by constructing a one-to-one full flow path three-dimensional model, we achieve an authentic representation of the internal transient flow dynamic of pumped storage systems. Accuracy, our simulations are designed to keep errors within a tight 3% margin, ensuring high reliable and precise characterization of hydraulic behavior. Precision, through the use of high fidelity models, high resolution grids, and advanced turbulence modeling techniques, we can accurately capture the multi-scale turbulent structures present in the flow field. Next, I will introduce the three-dimensional transient simulation technologies. The construction of a multi-scale full-flow path geometrical model forms the cornerstone of our simulation and optimization efforts. We employ a multi-scale coupled modeling strategy, constructing the complex multi-scale flow path structure of a pumped storage power station at a one-to-one scale. This allows us to capture every detail with precision, ensuring our simulations are both comprehensive and highly accurate. In strict adherence to design blueprints, we parametrically reconstruct kilometer scale, long distance water conveyance systems, meter scale, critical flow components such as the spiral casing, stay and guide vans, runner, and draft tube, millimeter scale structures, including the wiring ring and clearance gaps, ensuring high geometrical accuracy in both stationary and rotating components. By sampling these precision multi-scale models, we achieve seamless integration from kilometer scale waterways to millimeter scale clearance, fully preserving the geometrical characteristic across various flow path scales. This approach establishes a high fidelity geometrical foundation for the subsequent simulations. We are dedicated to achieving a high-resolution grid that optimally balances computational efficiency with numerical accuracy. First, we employed a domain-specified hybrid mesh strategy. A structured hexahedral grid is applied across the entire runner domain, ensuring that the wall adjacent y plus value remains below 10 to accurately resolve the boundary layer velocity gradient. For the guide vans, the mesh type dynamically adapts according to the motion patterns, retaining hexahedral grids under steady state conditions for computational efficiency. While transitioning to wedge shaft meshes during dynamic deformation. This dual approach ensures optimal resolution of shear layer while providing the flexibility needed for the adaptive reconstruction, balancing accuracy and performance seamlessly. Additionally, we focus on constructing a smooth transitioning mesh topology, which enhances numerical transmission efficiency. Second, to accurately capture the multi-scale flow dynamic driven by the model's intricate geometry, we employed a multi-scale mesh coupling technique. Transitional meshes are strategically placed to ensure smooth numerical transitions between flow passages of varying scales. For instance, large-scale meshes are applied to the guide van and the runner regions, while fine grids are used in clearance regions. Transitional meshes characterized by high aspect ratio elements are employed between these regions. These meshes maintain the large-scale grid resolution along the mainstream direction while refining the perpendicular direction to align with the gap scale mesh. Finally, we applied the Richardson extrapolation method to validate grid conventions across different mesh densities, enabling us to determine the optimal grid resolution. The final grid selection minimized computational resource consumption while ensuring that simulation prediction error remain below 3%. To address this substantial geometrical deformation resulting from the dynamic adjustment of the guidewires, we employed a hybrid algorithm that combines elastic smoothing and local mesh construction. To handle mirror adjustment in the van opening, we rely on elastic smoothing, which use a spring-based axiomation to preserve the mesh topology. However, when the opening variation exceeds a certain value, local mesh reconstruction is triggered in regions experience substantial deformation. This dual strategy ensures the preservation of high mesh orthogonality throughout the van motion, with mesh quality consistently maintained above 0.3. Besides, we are committed to the independent development of transient process solution methods for pumped storage systems and have created a composite user-defined function, the UDF, that integrates 4 major function modules. First, we implement customer boundary condition functions, enabling real-time input of dynamically changing boundary condition for precise simulation control. Second, by invoking dynamic mesh. Okay, sorry, I shut down the software. By invoking dynamic mesh techniques, the angular variation of the guidewires is mapped in real time to mesh node displacements, allowing for the coordinate deformation of millions of mesh elements. This process accurately reproduces the dynamic regulation of the guidewires from fully closed to fully open positions. Additionally, by defining the torque balance equation of the unit and obtaining the runner blade torque and speed from the previous time step in the numerical simulation, we calculate the runner speed at each subsequent time step, enabling real-time monitoring of the runner's rotational speed. Finally, a rotational speed guidewire closed loop feedback algorithm is embedded within certain transient process calculations. This advanced algorithm, based on the time-dependent variation in guidewire opening, use a fuzzy PID control method to continuously adjust the runner speed, forming an electromechanical closed-loop control system. This integrated UDF framework provides critical support for the personalized simulation of transition processes in pumped storage systems. In the two-phase flow simulation, for the two-phase flow in the surgeon tank, we use the volume of fluid, the VOF interface tracking method to accurately capture the changes in the air-liquid interface as water levels fluctuate, capturing every details of the dynamic change. For the two-phase flow within the unit, we apply the mixture model or the Euler-Euler multi-phase flow model, utilizing interface force equations to analyze the transport of cavitation bubbles. This approach enables us to identify the inception points of cavitation during the transient process of the pumped storage unit. By employing the advanced simulation techniques outlined above, we have developed a comprehensive transient simulation methodology for various complex transient processes in pumped storage systems. This methodology enables the simulation of transient processes such as startup, shutdown, load rejection, and pump-to-turbine transitions for pump storage units. Next, I will present the analytical methods developed by our group. The first method we developed is vortex identification and analysis based on rigid vorticity. Vorticity are very common in fluid dynamics, yet a precise definition remains difficult. In classical vortex dynamics theory, vorticity magnitude is often defined as the intensity of the vortex or its rotational strength. Vortice and vorticity are often equate, but research has shown that there is no inherent correlation between vorticity and the fluid's rotational intensity. In fact, according to the theory of vorticity decomposition, vorticity contains components that represent both the rigid rotational motion of the fluid and its anti-shear motion. Only the former can truly characterize vortex structures, which we refer to as rigid vorticity. In simple terms, the extraction of rigid vorticity involves decomposing the velocity gradient tensor in a Galilean invariant reference frame, thereby uniquely determining the rigid vorticity that accurately represents vortex structure. Based on rigid vorticity theory, we have verified its applicability and advances nature within pumped storage units. The left figure shows the vortex structures identified using the rigid vorticity method, while the right figure displays the vortex structures identified using the Q criteria method. It is clear that the boundary of the vortex structures in the left figure is sharply defined, whereas the right figure reveals numerous sheet-like vortices in the near-wall region. In fact, these near-wall flows exhibit only strong shear effects, and the region vorticity method readens these sheet-like structures with near zero region vorticity, accurately indicating that these regions do not respond to true vortex structures. Furthermore, we have developed a comprehensive vortex dynamic analysis method for pumped storage units, enabling a thorough investigation of vortex dynamic characteristics under different operating conditions from 3 perspectives: spatial quantitative distribution, temporal evolution, and the morphology and deformation mechanisms of vortex structures. First, we derived and constructed the region vorticity transport equation and the region entropy transport equation, both of which are compatible with Reynolds average Navier-Stokes simulation method. These two equations, on one hand, account for the impact of turbulent fluctuation effects, which are typically neglected by the RANS computational method on vortex evolution. On the other hand, the individual terms on the right-hand side of the equations represent the distinct effects of various hydraulic factors on the vortex structure, allowing for a more intuitive investigation of the deformation and evolution mechanism of the vortex structures. Additionally, we considered the influence of runner rotation on vortex structure evolution in a rotating coordinate system. To capture this effect, we introduced the Coriolis force term to represent in the initial effects. This case study investigates the temporal evolution characteristic of vortex structures inside a pumped turbine operating at different Galvan openings. So we can see the movie. Under low opening conditions, the vortex structures within the runner domain exhibit periodic evolution. Undergoing a cyclic process that includes stage of independence, growth, diffusion, and connection, helical deformation, and the rupture separation. In contrast, we can see this movie. It's a movie under the high opening condition. The vortex structures within the runner domain almost maintain temporal stability. Additionally, based on the previously proposed transport equations, we conducted studies on the vortex morphology and deformation mechanisms for both types of vortex structures. This analysis explained why, under low opening conditions, the vortex morphology exhibit a helical shape, identified the locations where vortex structures undergo separation, and clarified why, under high opening conditions, the vortex morphology remains largely unchanged. Furthermore, based on the cylindrical layer invariance assumption, we proposed a spatial quantitative distribution analysis method using a relative streamline coordinate system. This coordinate system overcomes the limitations of the Cartesian coordinate system in addressing the distort runner blade passages, enabling the quantification of variable distributions in the span-wise, circumferential, and streamwise directions. It provides an advanced technique for characterizing and analyzing unstable flow structures in rotational machinery. This analytical method has been successfully applied in research cases such as axial flow pump, flow field analysis, and vortex intensity spatial distribution in pumped turbines. Okay, next I will provide a detailed introduction to the practical application outcomes with a focus on engineering case studies. We focus on the need for rapid response in pumped storage systems within the context of new power systems. For the typical transient process from 100% pump load to generation at no load, which we call pump to turbine transition, we have developed an integrated research framework for simulating, analyzing, and optimizing three-dimensional transient hydraulic behavior. Firstly, we focus on accessing the feasibility of the simulation strategy for analyzing the hydraulic transient mechanisms. For the pump to turbine transient processes, we integrated the modeling techniques, mesh technologies, dynamic mesh methods, and UDF approaches previously introduced, enabling the simulation and reproduction of transient flow field behavior within the pumped storage system. Secondly, the traditional control process has significant drawbacks. The opening and closing of the spherical valve takes too long, severely affecting transition efficiency. I mean the transition rate. Additionally, the hydraulic stability of the unit during the pumped braking period is poor, with extended duration that pose a threat to the safe operation of the unit. To address this, we proposed an innovative optimization solution. eliminating the opening and closing process of the spheric valve, keep it stationary, and effectively utilizing the pump braking process. We discarded the traditional electrical plus mechanical braking method, and during pump shutdown, pre-opened the guide vents to a small angle. This enabled hydraulic braking, accelerating both pump shutdown and turbine startup. We refer to this new transient process as fast pump to turbine. We designed a coordinate guide vent closure strategy. When the speed drops to 50% of the pump's rated speed, the guide vents are pre-opened. When the speed rises to 50% of the turbine's rated speed, the guide vents are further opened to the turbine's no-load settings. Using this transition process as a case study, we explored the hydraulic transient mechanisms and conducted a feasibility analysis of the faster pump to turbine process. The study reveals that the optimized control process significantly shortened the transition duration while greatly reduced the pump braking period, thereby improving the safety and stability of the unit. Key parameters such as axial force, radiant force, and pressure fluctuations all remain well within safe operational limits. The most notable flow phenomena is the sudden variation in pressure and velocity in the vanless region during guide vent opening and closing. To validate the practical effects of this new convention procedure, we conducted the industrial verification on the 125 megawatt unit at the Hongping hydropower station in China. It's a pumped storage station. These results showed that the optimized convention process reduced the transition time by almost 50%, with all stability performance indicators meeting the design requirements. This achievement not only confirms the effectiveness of the optimization strategy based on the simulations, but also provides insights for future engineering applications. Okay, finally, we performed a deep optimization of the control parameters based on simulation techniques. The study found that the pre-opening strategy of the guide vents significantly influenced the transition process by increasing the pre-opening angle. The transition time can be further reduced. Similarly, advancing the pre-opening moment accelerates the speed reduction process and also contributing to a shortened transient duration. Specifically, increasing the pre-opening angle from 38.5% to 53.8% of the rated no-load opening shortens the transition time by an additional 11.1%. Advancing the pre-opening moment from 40% to 60% of the pump's rated speed further reduced the transition time by 5.62%. In all control schemes, the increase in pressure fluctuation amplitude does not exceed 10%, while the maximum pressure values which occur during the pump shutdown phase and are unrelated to the pre-opening of the guide vents remain almost unaffected. Okay. Furthermore, varying the pre-opening angle has minimal impact on the unit's actual and ratio force, while changing the pre-opening moment may worsen ratio force fluctuations. Therefore, we prioritize adjusting the pre-opening angle as the optimization method to improve both the efficiency, the transition rate, and the stability of the transition process. Finally, based on the previous research foundation, I would like to introduce the research topic we will continue to explore in depth. The first topic focuses on studying the mechanism behind local hydrodynamic load variations induced by multi-scale transient flow on turbine runners. We are dedicated to developing a quantitative, refined correlation analysis method that links multi-scale flow, local hydrodynamic loads, and runner force. By capturing the precise characteristics of the complex flow within the runner region, such as complexly three-dimensional flow, pressure distribution, and hydrodynamic loads on the blade, and the overall force on the runner. We aim to establish an analytical approach that enables the study of the relationship between complex flow and unbalanced hydraulic excitation force on the runner. This will allow us to explore the mechanism by which abnormal flow induces runner force instability, providing theoretical guidance for the development of flow control strategies. The second topic investigates the synergistic control mechanism between the transition rate and hydraulic excitation force on the shaft system, with the goal of revealing the refined control interaction between the transition rate and the hydraulic excitation force. While accelerating the transition rate in pumped storage systems is essential for meeting the great demand for rapid regulation. It also increases hydraulic excitation force on the unit. Our future research will focus on evaluating the impact of these changes in hydraulic excitation force on the safety and the stability of the runner shaft system. The aim is to accelerate the system's transition rate while ensuring the safety and the stability of the shaft system. Identifying areas where the transition rate can be increased without compromising stability. Okay, and last, I want to thank my PhD student Xiaotong Yan and Professor Hui Xiangchen helps me to prepare this PPT file. Okay, that's all for today. Thanks for listening.
Thanks, Professor Cancan, for this insightful presentation. The proposed fast pump to turbine transition method, from my point of view, is particularly impressive because it offers significant benefits for real-world hydropower operations. We have two questions from our participants. The first one is about rigid vorticity. I'm just confused that how to build the rigid vorticity and how to calculate it.
Okay.
So maybe slides.
Okay, let me find the slide.
Maybe 17 or 18. 15.
Okay. This is the slide for about the rigid vorticity. The establishment of rigid vorticity involves two steps. First, a principal coordinate system endowed with Gallia invariant is need to be established, and then within the principal coordinate system, the composition of the velocity gradient tensor need to be conducted by utilizing an organic transformation matrix Q. The original coordinate system undergoes a three-dimensional rotation, and this rotation aligns the z-axis, parallel to the rotation direction of the fluid elements. Next is the determination of the x-axis and y-axis achieved by performing a rotation utilizing the matrix P in the XQ, YQ plane of the aforementioned coordinate system. And this rotation is carried out at an angle theta, where the value of the theta is uniquely determined by the velocity gradient tensor. Through this process, the principal coordinate system is established. Subsequently, the decomposition of the velocity gradient tensor takes place within this coordinate system. And we calculate the reagent vorticity using the commercial software TechPlot and corresponding fortune code. And in addition, commercial software on this host also supports user to customize variables through user-defined programming. So for more information, every guys can read our published paper.
Very recent paper.
Yeah.
Mm-hmm.
So this is the reply for the first question.
Could you please explain what is the streamline coordinate system? So it's quite correlated. Streamline coordinate system.
Okay. Let me find this. Okay. This slide shows the concept of the streamline, and we can imagine that this is the mean camber line of the blade, which can translate in the circumferential direction from the blade suction surface to the blade pressure surface, and it can intersect with different span surface, and the interaction line is streamline of the current circumferential position and the current span position. So we defined the streamline coordinate as the for analysis. Yeah, that
question is from Misag Moradali. In the early slides, you discussed and compared the structured and unstructured grid to be used in the dynamic simulations. Did you observe any advantages in using either structured or unstructured grid in the dynamic mesh?
Okay, I see the question.
Mm-hmm. So you have to go to the first slides, maybe.
Yeah. Actually, in the simulations, in the numerical simulations, we always prefer to use structured mesh. But when we need to specify the rotation of the guide vans, the mesh need to be changed. So we utilize the function in front of we use the dynamic mesh techniques in commercial software front. The mesh need to be reconstructed, so we can only generate unstructured grid. So also we also read some papers use structured grid to use structured grid in the mesh, in the motion of in the movement of guide vans. But the disadvantages, I think, is it's very hard to it's very difficult to simulate when the opening of the guide van is very small. So when we besides when we use the unstructured grid, we also test the accuracy of the results. So this is the experience and our from our studies.
Okay, we have other two questions, but maybe it's too late to answer directly. So maybe Professor Cancan, you can answer after during the presentation of Professor Enrique Cabrera by writing the answer of these two last questions. Thanks again, and we can pass to the second speaker and the second session chaired by Jose Vasconcelos.
Okay, well, I hope you guys can hear me out. And we, again, would like to welcome everybody who have joined. And we're now going to begin our second presentation of the day. And it's really a big pleasure of mine that I am introducing here Professor Enrique Cabrera. Professor Cabrera has a very long history of contribution to hydraulics and transient hydraulics. He has graduated as industrial engineer in 1970 and obtained his master's in physics in 1974 and PhD focused in water hammer in 1976. So Professor Cabrera started at the Polytechnic University of Valencia in 1981 and continued there to this day. And in 2019, he became emeritus professor at Polytechnic Valencia and has over 5 decades of work in being involved in various fields on urban water and pressurized flow transport, have had contributions in hundreds of journal papers and dozens of books, and really have had a tremendous impact in our field. And he's going to talk about one of those contributions today through his talk on the software called IAHR. IAHR is a transient, easy to use, user-friendly application to study closed pipe transient flows. And really, through so many contributions, I'm looking forward to his presentation today. And I really would like to thank again Dr. Cabrera to come and share his knowledge with us. Professor Cabrera, the floor is yours.
Thank you very much, Jose. Let me show you my, let's go. Are you seeing my screen?
No.
No? Now, are you seeing my screen now?
Yes.
Yes. Yes.
And you are listening to me?
Yes.
Well, in that case, I will start. Well, it's my pleasure to be here with you. This presentation is addressed mainly to engineers and to consultants. I want to present IAHR, a software that is now used by thousands of people all around the world. And I will try to show you their capacities much more than its background and the mathematical support. Here you have where you can download it. You put this address, and later on you ask for a code, and they will send you a code, and you can use immediately IAHR. We say that it's a Latin software because its origin is from Brazil and Italy, and for sure Spanish as well. And it's a free software. My presentation has been split in 7 points. First, an introduction to explain you where when is born a baby and how and when has been developed. Later, the main capabilities of a baby. Later on, I think it's very important from my experience that people cannot calculate transients if they don't have a good understanding on the physical phenomena. And I show you how a baby can help to improve this understanding. For me, it's very important. Later on, we will go to the main application of a baby to calculate transients and to select and science protection devices to have a safe pipe. Later on, it's a very interesting thing to use a baby to explore how can pumps as turbines use it. Later on, just presentation of a tool for complex systems, because the first part of the presentation is much more addressed to simple pipelines, and finally some conclusions. If you have finally some questions, please send me the questions by writing the questions, because it's much easier for me to reply to these questions. Well, this is the basic. It's a free software package, and this friendly, it has been, as far as the main menu has been inspired much more in EPA.NET, so you will see very similarities, just speaking about how to download, how to create a file, and so on. It's in Spanish, for sure. Here you have the screen in the Spanish. Portuguese, because we have very strong roots with Brazil, and in English, for sure. So it's very easy to change the idiom, the language. You open this screen, and later on you push Spanish, English, or Portuguese, and all the screens are projected in the corresponding, in the selected language. Just a little bit about the story of Javier. It's a joint venture between Professor Edmundo Cueve, from now is passed away from 3 or 4 years ago, and Ita, and well, we have been, and here you have Lorenzo Avievi, the Italian man, and here is not an Italian, very friend of mine, that also passed away 2 years ago, is Michele Fanevi, is very good expert in dams, but as well in transients. Well, Avievi needs, it's a joint venture between Professor Cueve and us, started in early this century, and we have developed in Valencia, led by Professor Espert. You have here Espert, the forefathers of Avievi. And well, now, as I said before, we have about thousands of people using Avievi all around the world, but one expert can manage by themselves if has a good knowledge about transient phenomena. But there are many engineers that don't have the background, and we are providing online teaching course, all in Spanish for the moment, and we have about 300 to now 400 people that has followed this teaching course. The course that we are learning is a platform online. We are speaking about Cursos Agua, and that part of Cursos Agua is on transients. And we provide, for sure, the Avievi for making practices. And this expert in transients has 4 courses different, one of basic hydraulics, this second course for the basics, ideas, the fundamentals of Avievi, Later on, you have how to size, how to select protection devices. And by the end, we have here the last course for more complex case studies, more complex project than people who is following the course are interested on. By the end, we project, this is first the final check of the project. Some 10 years ago, we calculate that the data, this basin transfer, here you have the main characteristic of the transfer. This is the investment that they did, the amount of water to be transferred each year, the length, the pipe diameter, and the maximum flow that may circulate. As you can see, it's a rather irregular profile. All has been calculated here. And well, you here have the map of this intertype, this pipeline to transfer the water from here to here, and has been well documented in this book that we nominate transitory hydraulic transients from the steady state to water hammer. Because we'll explain it a little bit, but this is a book where more technical details and more practical hidden details of the IAHR are written here. So in 1 hour, I have no time to go in details, just to show you the main characteristics of this software package. It's mainly focused in water transport system, pressurized. Also can work on open channel and hydroelectric power plants, but as the majority part of users are on pressurized water transport, IAHR is much more focused on that, on this area, much more than on open channels and hydroelectric power. It has less capabilities in those applications. Well, IAHR is being used 30 years ago because, as I said you before, the early first draft of the IAHR was developed by Professor Kelly at the end of the 20th century. But it was software for his particular use, and we developed and make it friendly during this decade. Well, we are going now to present basic features of IAHR, what we can do. As you well know, the equations for hydraulic transients is the continuity equation and the momentum equation, and we use, as most of the software packages, the method of characteristics. As you will know as well, we need boundary conditions at the end of the pipes, and IAHR works and can work with such boundary conditions, tanks, pumping station, etc. The most common situation, change of diameter. When you have a pipe and node with a change of diameter, it's a boundary condition as well. So it considers most of the practical cases you can find in the reality. When you come in IAHR, you will see 4 different menus. This is the main menu, but basically it's very similar to an EPA net. The selection of the different elements that integrates the system is very easy and very easy to draw. Air valves does not appear here because are linked to pipes. You should go to the pipeline, and later on the pipeline you can include the air valve. The basic menus, we have 4 basic menus. First is the image menu. You can see this is for drawing the system. you have here, you can find all the elements you can find in practice. For instance, you go to the valves, and here you have a display. You can find the different types of valves you can find in practice, air vessels, etc. If you have with a bladder or without bladder, you can select the appropriate air vessel you are using. This is the first image that you can find. The view is, well, to put labels to build the image. You have width or height. You can select here the characteristics. And well, even the panel of data, you can list here which data I have logged to the program. This is the third menu, the most important one, the project. Here you have the options to calculate. For instance, you have here the time of interval, it's 0.05. The characteristics, if you want to change the fluid, so you have the main parameters for calculate. One important thing in a VFB, I think it's not normal, is that prior to calculate the transients, you must calculate the steady state. The steady state we calculate with the method of characteristics as well. So it's important because if you put some data wrong, you can check when you after calculate the steady state, you can check if you are putting the system that you want to put, because you can see the velocity, the flow, etc. You can see the results of the steady state, and once have been calculated, you calculate the transient. Obviously, to calculate this, you have not decided which kind of perturbation you introduce. For that, you say which pump stopping, pump start, valve closure, etc. And later on, you calculate the transients depending on the valve closure you have introduced, the law of closure, etc. This point is very important as well because you can see in a graphical way. For transients, you can see the images, you can see the evolution of the pressure in a node. You can simulate the envelope of one pipe, minimum and maximum, but obviously for a steady state, you only have a table showing the velocities, the pressures, and so on. But you have not graph possibilities because you don't need for the steady state. And finally, the settings, well, for instance, in the setting for the screen, you can see we are going through this main selection. Where you put the setting, for instance, you see here the language, you press this button and later on you select your language. Options are the options for calculation. You have by default the interval, the time of interval for the transient analysis, usually 0.05 seconds. That means that for a wave severity of 1,000 meters per second, you will analyze 20 points, but you can analyze more points if you make a time interval for calculation smaller, etc. But you have here the options. And well, this is for the code that I send you when you ask for a license. We send you a code and immediately you can use it. So this is the final screen for such a kind of options. Well, always here in this setting, you have database of different valves. You can put valves previously selected, so you don't need then later you don't need to charge the characteristics. You can also give pump characteristics, and later on you don't need point by point to include that, so it's a very convenient feature because it makes the calculations more fast. Here you have more things. Well, we can import files from EPANet and from AutoCAD. So if you define your own system, you go here to New, and you select your own system by the screen number 2 that I have shown you before. But if you have a file already, for instance, a file created by IAHR, and you take again that file to analyze again, you can obviously go to this file created before, or you can go to a file in the EPANet or a file from AutoCAD. You must take care when you import such a kind, because some data that need IAHR are not included in EPANet, for instance, the wave severity, but well, in the manual you have all those details to proceed accordingly and don't make mistakes. As I said you before, prior to proceed with the transient analysis, we need to calculate the steady state. Otherwise, if you try to calculate the transient analysis and you have not performed the steady state, IAHR will remind you that you need to make prior the steady state calculation. And this very interesting thing is you have here assistance. For instance, many times when you are calculating a pump line, you don't know the inertia of the rotating parts, the inertia of the pump and the electric motor. So here you have an assistant that can help you to estimate the inertia of the whole system, or the same if you don't know the wave severity. For sure, you can put directly, you select the specific speed, or you can calculate the speed, saying which kind of material are using, and in that case, the calculation, IAHR performs the calculation directly. So such a kind of assistance are quite useful for when you don't have data not so current. Other features you have here. This is very important as well. The scenarios. When you have a pumping line, you don't have which kind of air chamber you must use, which size of, perhaps you can use air valves. So you can put the system and you can select different protection device, and you can select now is working this one, now is working that one, or they can work simultaneously. In any case, we will see that later on. I said you that air valves must be included through the pipeline, and even most of you know that the main transient that you can find in practice, is the break of a pipe. So the flow is increasing dramatically, and if I want to design a valve that control the main velocity, well, you can make this calculation. You can see how higher can be the velocity if that pipe split, and later on you can. This is very important to say the impact. And last, IAHR can change as well the units. Currently in Europe, we use the international meter, second, and kilo. But if you are using the other system of units, you can change it easily. And this is a very important thing as well. many times when you are designing a system for the first time, you don't know which kind of pump you are going to install. It's different if you have an installation that you are reviewing. In that case, you know the pump characteristic of the pump. But in a new installation, you have not decided yet which pump I'm going to use. Aviary includes 14 universal cams, 14 because depends of the velocity, the specific velocity of the pump. You have 14 different ones in case that you define the best efficient point through that can get you from that velocity, from that data, the velocity, the characteristic velocity, in that case interpolates between the two velocities that are included in Aviary. So you don't need to put inside the system my pump characteristic. Aviary do it for itself, but if for sure that you have the system working, you can put your real pump. If you connect the pump in the opposite way, I will show you later, Aviary knows that the pump works as a turbine. Aviary knows that this pump will work as a pump as a turbine. So that is very important because I will show you later in a case study. When you have a path working, you have many change of a steady state from one steady state to another one. And Aviary allow you to know the transient between one steady state to another steady state. So it's very useful always because this application is increasing in the last years. Aviary can calculate, take into account cavitation or not. In any case, if you select no cavitation, well, they don't take into account that the down pressure cannot be below minus 10 meters. But my recommendation is that never one pumping line must work under the pressure. So perhaps what you know that you have down pressures, you put the protection device adequately to avoid cavitation. Because models to calculate cavitation are rather complex, and most of the times you cannot believe in the results if you include the cavitation as to calculate that. Well, the graphic interface is very friendly. Yeah, if you use it, you can immediately take constate that is verify that the graphic interface is very easy. It works very well. No matter a simple or complex system, you can calculate transients in a network perfectly. The type of fluid can be changed as well, and you have animations as well. Obviously, you have animations when you select a pipe to see what is happening in that pipe, because in a node, it doesn't matter what the animation. In a node, you have the evolution of the pressure, but in a pipe, it is plenty of sense to see the animation because you can see how the wave is traveling along the pipe. You can hear the simulation and you can see in which way waves are going up and down. Well, this is a very short presentation, 1 hour is, but just to put the focus on the main characteristics. If you want more details, you need to work on with Aviary. As I said to you before, a good engineer, a good consultant cannot perform hydraulic transient calculations without a good understanding of the transient. And Aviary can help you to improve. And as I am a teacher, I give a lot of relevance to such a kind of physical understanding. You know that a VAB is a computer-aided design tool, but sometimes if you don't know well the phenomena, CAD can become computer-aided disaster. Why? Well, it's very easy to forget 1 0 or to put 1 0 more. A good engineer must have very, let me say, order of magnitude of the different variables. Well, the software package works very well, has been checked for many years. Even many times somebody asks us, I am using that program, it's very expensive. I am exploring the possibility to move to a VAB. Can I be sure what we do in that case is calculate in the software that I have that the asking person is asking to us, and we make the same, replicate the calculations, and we have compared a VAB with, can say, easily 5, 6 commercial packages, and the results are quite similar. So we have that example. So we are very confident about a VAB works, but I'm very confident if that are good. If that are not good, we cannot guarantee nothing. For such, it's very important for me, very, very important to have a better understanding, a good understanding of the transient phenomena. Here's what I said before. This sentence is very, very Heraclitus 2,500 years ago. Heraclitus said, all things are in motion like a stream. That you know very well. If I compare my picture now and when I had 20 years, I believe that I have clearly that all is in motion. From one day to another one, the change is minimal. But you have here the hydraulic models. You have here the rate of change. You have here the elasticity of the system. You have elastic model, that is to say, water hammer, if you are here, depends on how fast is the transient and depends on how elastic is the system. Obviously, if the transient is becoming very, very slow, you have the quasi-static model that you know very well, then EPA-NET can calculate quasi-static transients, but this is a transient as well. A steady state analysis is just the theoretical analysis because always, like said Heraclitus, all systems are in movement. Well, we currently are here. Rigid model, you know that, well, change are fast transients, minutes, but, well, you have here what we say inertia model because we take into account just the inertia of the water inertia, but not the elasticity of the point. Well, we are covering here, but we are going from the steady state to the water hammer because we calculate here with a VAB, with a method of characteristics, and we can calculate any system. And for such, we put here the name from the steady state to the water hammer. And usually people goes to a VAB when it has a desire. If I have in desire, I will use obviously a panel. I don't need to go here. Main parameters, I need to know perfectly the role that these parameters using in a transient analysis. We know that very rigid pipes have a wave severity over 1,000. Very elastic pipes, like plastics, can have a wave severity about 300 meters per second. Here you have the 9 water hammer parameters. The elastic wave travel time is the length of the pipe until a change of physics divided by the wave severity, and the speed of change usually is a valve closure or a valve opening. This valve closure can be very fast or very slow. You have here, well, these are the boundary conditions. And here are very important thing is, well, that when I arrive from the perturbation is created in one simple pipe and arrive the perturbation to a node, you transmit the perturbation and the perturbation is reflected. That means that one single charge arriving to a node is divided in many charges. The original one is loose because part is reflected and part is transmitted. These coefficients are very important. Is the transmission coefficient, and this is the rebound coefficient. These expressions are very well known, so it's important I will show you later on one example. For me, it's very important to understand what happens when a charge arrives to a node, to a tank, to a valve, etc. And that is showed transient analysis, understanding. This is a very single system. This is the length, 10,000 meters. This is the wave severity, 1,000. So the travel time is 10 seconds. And if we put instantaneous closure, it's very easy in the IAB. You put the instant and you put the opening. So you say at 5 seconds, we are here at 5 seconds, is entirely open, and at 5.001 is completely closed. That means that in 1,000, it's closed. I go from totally open to totally closed. That gives a instant closure, and we arrive to very well-known simulation of the instantaneous closure. This is this point, and if you go to the middle point, this is the middle point. Obviously, like you have here 75, and in the node N3 you have 50, you are 25 meters of pressure less because the elevation. Obviously, we have here ideal system. That is in a way very easy. If you put in the pipe a roundness negative, a negative roundness, that is impossible. The roundness can be 0 in hydrodynamic, very, very small, but negative is impossible. But instantaneously, I really understand that I mean no friction, ideal case. Obviously, in a friction in real system, you can see the comparison between this system and this one. You are selecting here the package effect that every expert knows perfectly, the difference between this simulation with some friction and this simulation with any ideal. Again, if you make the closure fast or slow, the time characteristic is go and back is 20 seconds. If I close in a time bigger than 20 seconds, we have a slow closure. A fast closure, if the time of closure, see, I start to close here, and in 5 seconds, I close totally. Here, it takes 30 seconds for going from 10 seconds to 40 seconds. For sure, in that case, we have the maximum speed, the maximum pressure until 7,500. This is very well known to know which part of pipe support the maximum pressure. And in that case, like it's a slow closure, we can see that in no point of the pipe you arrive to the maximum Joukowski peak pressure. And this is a very interesting example from my point of view, is to understanding how a surge reflects and transmits. These pipes have different diameters. So in that case, N2 is a boundary condition because this pipe has I think it's 500 millimeters, and this one is 1000 millimeter. This is, of course, a theoretical case because it's quite impossible in two pipes in series this change of diameter, but it's very nice to see different transmission and reflection. When I am going to search by here on the right to the reservoir, the transmission is 0 because the search, well, it's very, the inertia of that time, but the reflection is -1. Well, this can be seen here. In that example, I am showing you, this is the AVAV maximum pressure, so you can find that, and you can see here, well, 2 seconds later, because it's the time from going to here and go back, and you have a different, you have the 55, the search arrives here, has a reflection and go back. This is reflection minus, this means transmission and reflection of surges going in that way. This is the reflection and transmission if the wave comes from the tank to the valve. Well, here I explain why you can find it's not easy to reproduce all the graph because each time arriving to a boundary condition, one surge is split in two, so you have, with passing time, more and more surges, and it's rather difficult to find where they are, how has reflect. But this first two slopes you can see perfectly well, and it's very easy. This is the downstream part. Of course, if you close here, this is an overpressure, and you have here a down pressure. This is the depression. In that case, you can see that you will find here cavitation, which is calculated without taking into account cavitation. And well, you can see here, but we can do the same that is in the left side. For instance, if you close in 100 seconds and you have a two-step closure, fast at the beginning, very slow at the end, well, you can see that you have not water hammer. The pressure in the right part upstream is, there are not overpressure, just small pulse of 5 meters, seem the same, and here in the downstream, again, you have not depression because you have 9 meters over 0, so you have not overpressure. Well, we are going to a next item, how to select and size protection device. This is a very conventional picture taken from this paper, and I show you because it's the typical profile with the most typical protection devices. Well, a bypass is very useful, but not for such a kind of system, because a bypass, when you have here the pressure open, but if you have here a level, the bypass only can destroy depressions until this level, so never can avoid depression over here. But it's okay for very flat pipes, can be a very interesting protection system. In the manual, if you go to the manual can be downloaded from the AVAV website. Well, this is the manual, and you can see well described which data you need for such a kind of boundary condition surges. Well, you will find here all the details. You have here pumps with universal characteristics, or well pumps with point-to-point defined when you have an installation working and you have, you know perfectly which pump is installed in the system. One thing that I am knowing now to show you is about the slum. Slum, how really can you prevent about the slum? Any of you, most of you, I think that all of you will know what is in a slum. I have a check valve, and if I have a pipe with a big slope, water stops immediately and goes down when the valve has no closure yet. The inertia of the valve is much greater than the inertia of the pump. So we have here characteristics, dynamic characteristics of different check valves. These are the worst valves because they have a lot of inertia, and this is the very good slum, the very good check valves. Obviously, when you move from here to here, are more expensive, but of course, they are react very fast. So, but I want to know in one given pumping station which kind of valve must I select. And the same happen with air valves. If the exit of the air is very fast, I have a slum because the air valve closes as well very fast. So a non-slammer valve has such a kind of characteristic. Well, it's very fast at the beginning, but right into here, see that well, the exit of the air, well, it's dramatically reduced in order to avoid an instantaneous closure of the check valve. This is easily a non-slam check valve. Here is obtained from different manufacturers. And for instance, if I am here this steep slope pipeline, we have 200 meters in 5,000 meters, so that means the slope is 4%. Well, for sure that you can find steeper pipelines than that one, but it's rather one. And in that case, you calculate the deceleration, dVdt, that in such a kind of pipeline you can find. Here you have the evolution of the pressure here at the node M3. Here you have, and here you have the velocity. The velocity, the initial velocity is the steady state 0.9. Here you have that the law of pressure said the pump will stop at 5 seconds. So until 5 seconds, nothing happened. But later on, as is a rather steep slope pipeline, goes very fast. In less than 1 second, the water stops. That means that the deceleration is the change of velocity from 0.9 to 0 in that time. So this velocity meters per second divided per seconds, I obtain this acceleration. Or in English units, you can find that one. If I have a mild slope pipeline, it's exactly equal to the preceding one, but now I have 20 meters and 5,000 meters. That means that the slope is 10 times less than the previous one. Obviously, I changed the characteristics, same diameter, but it's not exactly the same flow and the same velocity because the hydraulics, but I changed some here some friction at the valve that is here in order to simulate more or less the same steady state. As you see here, the pressure follow that way, while the velocity makes that. And at the end, closure dramatically here. But here, you can have just 0.20. That means that the deceleration is very, very small compared to the preceding one. So before 3.75, now 0.74. That way, you have the bigger deceleration, and you can see that the bigger deceleration is that one. This is foot per second. This is 3.75, almost 5. So you go here, you can see that you have slumps. So therefore, in that case, you could not use neither no one of these valves. But you can use that better valves because are you here and you have non-slump. In the builder slope line, you have this deceleration and you are confident that you have not slump, so you can install and you can be confident that such kind of check valves, we don't have problems with them. And the same can happen with air valves, non-slump and slump. In this case, we have simulated another system, and we have include slumps and non-slumps. Here you have different scenarios. We have provided 5 different scenarios. This you have not any air valve. Here you have 2 normal air valves. You have 2 air valves non-slump. Here you have 13 non-slump valves, and you have a binary closure longer than this one. And finally, you have a closure in 2 steps that is better. You can see and compare the different scenarios to see with a given protection which is the answer that you get. Here you have the profile of the system we are analyzing. Here we have 2 valves, first scenario with non-slump, and with non-slump here, with the slump here, and here you have an empty filter, 13, 1 air valve every 500 meters. Well, this is the one thing that they want to prevent if you use a VIEVI. There is an error. This is the only error that we are reported. The flow puts here cubic meters per second, obviously is liters per second. All these units are in liters per second. All is correct, but liters per second. Here also the characteristic, if this is the characteristic, is a current valve, this is a characteristic in an slump valve. A different air valve with the characteristics we put it in the simulation. If we compare a current valve and a non-slump valve, we will see different behavior. This is for the air valve inside the air valve, inside the valve. This is the same. Here you have the evolution, the valve open at mid-air, and the valve, this is the evolution. Here you have how is much better this behavior of the non-slump air valve with different behaviors. And the same in this case with the pressure inside the valve, not in the pipe. Finally, we compare what happened in the system itself. You have the steady state, maximum and minimum, the envelope of the minimum, and minimum is the green, and maximum, and this is the steady state. As you can see here, this is the profile of the pipe, and you can see here that you have a strong low pressure here and here. So in the other parts, the steady state is higher than the profile of the pipe. That is okay. but most of the parts of the pipe system, we have low pressures. So we need to prevent that. And we put 2 air valves, just 2. We improve a little bit the minimum. With non-slam, clearly is seen that is much better than one, but still we cannot solve the problem. If we add 13, one every 500 meters, we improve very much, but still we have here depression and even here cavitation. We should add 1 air valve here, another one to limitate. But take care if we know very well transients. If we make a closure, a 2-step closure, in such a way, again, 120 minutes, no more than that. But in 2 steps, very fast. The 20 per seconds, we arrive from 100 to 30% open, and later, from 30 seconds to 120, the rest of the valve. You can see that there is no depression, and even the protection that I have provided, the air valves does not arrive to open. We are not, in any case, the minimum pressure that we get, in any case, are below the profile, the pipe profile. That means that the air valve, in that case, no one of the air valves will open. So a big problem that we have only with a closure here in 2 steps, the problem is solved. So you can analyze and decide what we can do. And the same can be happen in a transient analysis with a pumping line. I have decided here different system protection. You can include the scenarios. This one scenario is no protection. This is a protection with bypass. We work very bad because the bypass only provide protection for this part of the pipe, the rest no. Later on you provide the one-way tank. Again, the protection will not be good. This is an air jump. Finally, you have a good protection. You have the same program, the same file, and you can simulate all the skies simultaneously. First scenario, no protection, no bypass. You will see in an installation you have in a pump station, there is a valve, yes. There is a check valve, yes. No bypass, no. Valve regulation, yes. This is automatically included in a VIB, and you only say check valve always yes. Valve regulation, it depends. Bypass, it depends, but you decide that. So depending on that, you select the scenario that you have. And here you have curve universals. You use the universal curves. You don't need to put that. And this is the optimal point to universal pumps decide which is the curve you select. Here you have the first 2 scenarios. You have provided here the bypass, and as you can see, you improve a little bit the depression, but it's impossible because the slope of the pipe only provide protection for the first meters, no doubt. If we connect, well, you have here the evidence that you bypass never can work, because if you have 25, the water can arrive up to 25. So you only protect this part, and it depends very much because you can find here pedalosis and so on. If you have here a dimensional tank, you active, this is a scenario 3, but you active this protection device, and what you find here is very good protected. The final part of the system had no protection in the previous part of the pipe. Here you have water hammer important, and you have that of the screw is in deep depressions. And this is the tank water level. This is showing the water level inside the tank. You can select in the possibilities to build that. And well, the tank initially had 5 meters, arrived to 4.66. That means that, well, this tank is oversized. If we protect an air vessel, this is a scenario 4, we active the air vessel, here you have the characteristics. In that case, you will see that the air vessel is in F, but it's a little bit just because the water level arrives to almost 0. So you know that is not convenient, because if you go here, that means that the water comes into the 2 point of the bladder. It does work well. So, but being looking at the envelope, the valve, the air chamber works very, very well. You have here only 25 of overpressure, and you have the minimum pressure. You have here some pressure, but in any case, you have cavitation. Also, it's important to avoid this depression. Well, you can put, if you select a chamber, push one-way tank, in that case, everything was okay. And you can think, well, instead of spending much money with a water tank, you can put 2 air valves. Well, the answer is again correct. Perhaps that is better for sure, but you make a cost-benefit analysis to decide if you opt by fixed selection on the other one. Well, I'm very close to 10 minutes, but I will show you what WAV can simulate paths and what happened with path. A path is a PAT. It's installed in water networks. And what is the main characteristic of the water network? The fluctuation of the flow and the evolution of the head. So a pump working as a turbine need to work very close to the best efficient point. So you cannot work at 100 meters per second at the best efficient point, and you can admit 200 meters per second. That does not work. You must be near to the best efficient point. That means 100, 110, 90, but you must move all around this point. And the same happened with that. So you can hear different possibilities. You can be here higher, and you need to regulate that in order to be sure that the will work in the adequate conditions. So that is taken from papers from PATS. You have here the reference of this other one. Full scale PAT means that as is established in practice, you usually have one control valve and one flow meter. This is a control valve to regulate the flow and a pressure regulating valve to control the pressure. And the pad is here. So you have these parallel lines to guarantee to be sure that the pad is working with the flow and the pressure adequate. Well, I can simulate exactly, I can replicate this system with that system. Here you have details using the universal, that is for sure. But what is important is to install the pump in the opposite way in order to tell you a bit that is installed. Well, you have here different scenarios depending on which system I am using, which of one test I am using, and you have the results. Here you have the scenarios. In that case, we use, in this case, this valve in order to simulate the pattern demand of the network. Here I simulate a sinusoidal or, well, a valve in order to change the flow and to change the pressure. So this is the way that I can simulate, but I can put any other curve and you find it here, the flow in the adequate system. I am running to the end by that. I'm going faster than I was. Here you have the flow through the path in the condition, and here the power that, as you can see, is a negative power because it's the power that is taking off of the hydraulic system, and you can see if that arrangement is okay or not, because you can compare if the flow is under the limits. Here you have approximately 145. This is 128. Will be on the limit. The variation, 10% more or less, perhaps it could work. And if a system scenario 4, scenario 5, you can select that. And in the end, as I said before, in 1 hour or 1 hour 10, I have no time to explain in detail. I am trying to show you the enormous possibilities that Aviavi has. I am showing you that it works again in complex systems. This is a very nice and refreshing image. It's a city very nice on the Mediterranean Sea. It's called Javea. It's very nice city, touristic in Spain. You know that my country is very touristic country. And well, the system is very heavy. You can see here the mountains close. Is a very big water distribution system, 30,000 people in winter, but over 100,000 people in summer. This is the length of the term. This is the system that I studied with Aviavi. As you can see, many decades ago, 3 or 4, they had a system. It's not a very efficient system. Here you have 94 meters. Here you have 13. You have almost 80 people, 80 meters of difference. So you take off the pressure loss and you arrive here with 75 meters. And here people decoupled this system from this other one. So we depressed that. For course that we can install a part to trying to recover that, but it's much better to link those systems and to pass to here. But obviously, you have water hammer here, because one thing that we have done, initially they pumped with the same pumps to different levels. We decoupled that one for the upper one. This is for the lower one. But here we have a regime. We have another. These systems are going down and up. We close that. We open that. So we have transients here. And we need to analyze that with Aviavi. We did that. Here you have the system, the integral system that we simulate in order to be that it's okay. And finally, this is the tile of the modified pumping station. You have here the 5 pumps, one to this pumping station, the other one to this one, and all linked. And finally, you have the results. Sorry, in Spanish. You have here the air chambers in the downstream, so in the aspiration. This is air chamber in one pumping line. This is the other one. That transformation was made 10 years ago. And here you have the saving in euros, but even it's more because that means that we have cut by a half, but in reality it's more. But in this year, the consumption was 10% higher than here. So we saved a lot of money in pay period less than 2 years. I guess that many years ago, engineers, well, they are not confident how to calculate water hammer. We did that, and has been successful. And 10 years later, we are not any notice about any problem here. And we arrived at the end, and it's my closure time as well. And I think that all that is written here has been explained. It's a friendly software, very friendly. I can show you. You can see that it's very friendly. It takes us 1 decade to be 3 or 4 people team. I will try to make a friendly presentation as well, showing the features and some examples. What I want to, well, I am confident that if you are a good expert on a good expert in transient analysis, you will download the catalog, the manual, and you don't need help. You can manipulate a VAB by yourself. Probably people who is a consultant or who are not aware on transient analysis need such a kind of tutorials. We give tutorial, and we give tutorial for people who follow our courses. When you download the software package, you ask for a code. Many times people ask, I don't receive the code, and this because your system refused that our email because problems on contamination of your system. But you ask for us, we will say, please stay in your server, adapt your server to receive my email. Well, that's all. I think that I arrived to the time, Jose, and I will be pleased to answer. Well, I have 8 answers here. 8 questions.
We have a lot of questions in the presentation. I think that indicates how engaged our attendees have been. I don't know, I have some questions of my own, but let's see if there's time for all that. I'm going to read the questions to you, and some of them are more theoretical, others are more about the software itself. For instance, is there any connection, any integration between Alievi and AutoCAD?
Okay, yes, you can download a file from AutoCAD to Alievi. I said that, and you can see one of my first slides indicating that.
Okay, good. Second question.
But be clear, because some data that you need in Alievi are not in AutoCAD. So you need to take care and to review what the file you have imported.
Yeah, I imagine that. Should be careful setting up.
You take a lot of you have a lot of work saved because you have the system itself is already in Alievi.
Yeah. Second question that we have here is, could you specify a little more the limitations that, and this question comes later as well. What could be potential limitations of using Alievi in the context of hydroelectric plants?
Well, they installed only a Francis turbine. So the invitation, for instance, we have not installed a Pelton. Perhaps our demanding is people from pumping stations and so on. So we have worked less such a kind of hydroelectric. I suggest that people more interested in that can go to the manual and they will read there exactly what they can do with hydroelectric power plants, much more than I explain you such question.
Okay. Okay.
Please go. I send the people interested on to download the manual in English, and you will find there 4, 5, 6 pages explaining him what the capabilities in such a kind of application.
All right. Again, I think there's going to be a second question on hydroelectric plants, but moving on in the questions, and I don't know exactly, but this may ring a bell for you. When using the rule as a demand-based pressure, does Alievi consider this behaves as a leak, or this could be taken as a leak model? I don't know if the question is.
Alievi, I know that you can simulate breaks. Break. I never applied Alievi to a leak, but I think that it's easy if you go to the feature brick, and because you are sizing the brick, with the variation of head losses to the brick. So if you go to the brick and you simulate how much is the head loss across the brick, you can simulate it perfectly.
Yeah. Okay.
So you can, I suggest who is asking that to go to the manual to the brick simulation. Later, a brick simulation depends on how big is the brick, because you know that there is a brick, total brick, or you have a longitudinal brick. So you need to say a BAB, which is the damage of the pipe, and we inform to the BAB about the damage through the head loss that the system finds in such a brick or in such a brick.
Okay. The next question is there a detailed help file?
If there are what? Excuse me, Jose?
The next question is
Yes.
whether Alievi has a detailed help file. I mean, there's a manual, but do the software itself has a help in it?
Well, for instance, when you are, for instance, you are in a pumping station and you forget and you calculate the inertia of the system, the whole system, because you don't know previously. And later on, you change some characteristic of the pump station, and we immediately say, please review the inertia. So you can, in different points, when you, or for instance, if you put a pump that cannot elevate the water so high, Aviavi will say this pump does not work. So when you put some data wrong, Aviavi inform you about that. But only if the system does not work, if you are wrong, but the system wrong, if the system works in a different steady state, Aviavi does not inform you because that is your problem. So if the system works, Aviavi never say you messed with your judgment to see if the steady state that you are expecting from Aviavi is the one that you are expecting. So you must review that. But if the system works at a different point that you expected, Aviavi does not prevent any warning because the system works.
Well, next question was linked to, well, what is the convergence criteria? I'm assuming that convergence criteria here would be maybe more linked to boundary conditions. What would be the typical convergence criteria used in Alievi then?
You can change the convergence criteria and the current condition as well. So what you must go is to the setting. To the setting is a screen that I have projected before, and you stand there. Which kind of, for instance, you have a network, and perhaps 0.05 seconds is a longer time for a very mesh network. So you can go to the setting and you can change the convergence criteria. Even you can say how many iterations you allow to Aviavi. You can say 2,000 or something like that. So that is again explained in the manual because it's very important question, this one. But if you go to the setting calculation criteria, you can adapt that criteria depending on, for instance, if you put small pipes because you cannot connect directly all the devices, you need a pipe separating. You put a pipeline, a pipe, a segment of 10 meters. So it's not a pipe of 10 meters because does not exist. You put the severity 0 because in that case, you consider that like inertia effects. You don't consider the elastic effects in such a kind of things. I am sorry because I cannot come inside such a kind of detailed applications of question theoretical, but I suggest again that they download Aviavi, download the manual and go to the setting and can see that all these questions are treated in deep, because many times users ask what is happening here, and many times you need to fake face to such a kind of questions.
Okay. I think the next question was already answered, but I'm going to read it again. It was, again, limitations when you're thinking about Allievi in the context of hydropower systems. I think the question is, can different types of turbines be modeled in Allievi, or
just Francis Quintana, Francis turbine. I'm sorry, because I said that at the beginning of my presentation. This is software packages mainly thought for pressurized systems, not for hydropower. Well, hydropower is as well a pressurized, but it's a different application.
Yeah. Okay. Now, two remaining questions here thus far from our the attendants, and then we have questions also from the panelists. Now, is there a way of adjusting the minimum time step to visualize results? Say, for instance, if you want to have a lower time step to visualize results of 0.1 second, is it something that could be adjusted in Allievi?
Well, in the settings, you can say for how long the transient must be calculated. So you say 250 seconds, 200, 300. There is no any limitation. You can extend the period of calculation as much as you want. No problem about that. But you must go again to the setting when you establish as a kind of
the time step, and the time step of writing results can also be adjusted, I would assume.
Yes, the time step as well, because perhaps usually you have 0.05. That means that for a wave severity, you are analyzing a stretch of pipe every 50 meters. If you pull that, or if you put delta X equal to 50 meters, you, for 1,000, you are analyzing every point every 50 meters. But you can analyze most points if you make shorter the period of time of analysis, that you can change again from the setting.
Okay. So the last question here from the attendees, there is actually a three-part question. The first part is actually answered on the answered questions on the Q&A, because there were questions related to, okay, how can a method of characteristic solver achieve steady state? And I tried to respond to that when you were going through your presentation. It's because you're setting the boundary conditions to steady as well. So the internal nodes would become steady with the solution of the method of characteristics. It's not Hardy-Cross, it's not Newton-Raphson.
No. It's using the same
set of equations.
All the method of characteristics, we are showing that from a steady state to Waterhammer, equations are the same, and the method of resolution as well. So it's not a software thing in very, very big networks, because, for instance, the sample that I have showed you in Javier, later on we consider only the main pipes, not all the distribution pipes. So it's thing for a network, but not a big network like a current water distribution system.
Yes. And I think the second part of the question, in which I think you answered to, does Allievi has pressure reducing valves? And it does.
Well,
it's
I think that Allievi includes all the different classes that we have. For each kind of valve, we have at least 6, 7, 8. I cannot remind. We have for flow control, for pressure control, for any. All the valves that we have found in the practice have been included in such a kind of application. Allievi is very strong.
Yes. The third question is: does Allievi have a package to simulate entrapped air pockets in the solution?
that is very complex because air pockets does not come inside the pipe in order to don't confuse about the calculation. We include the air pockets like stored by the air valve. So if air valve is admitting it's including air, you are increasing the volume inside the system, but not inside the pipe, inside the space of chamber, because otherwise it's quite impossible to modulate that. So you put the air inside a tank, close a tank, and you are including, and later on when you are expelling out this, well, you have seen 2 or 3 slides when you saw how many water air volume will come inside the pocket, but not inside the pipe in the modulation of the calculus. No.
So there was a further question since we started here. Actually, how you contact to obtain the software license. This is a question that is already answered on the Q&A. There is a web address where you get in contact with.
No. It's very, very easy. You go to the main page of Avievi. Just putting Avievi, you will find the web page of Avievi. So even you have there a button saying download the program. So you download the program and you download the manual as well if you want. Later on, the only thing that you must do is to write an email. You will find we will ask you some data. Who are you? Where are you from? Etc. Questionnaire. You fill the questionnaire. You send back the questionnaire filled, and with an email, and we send you again the code that you need to calculate. It's quite easy. It's very easy. Well, if you ask for that in weekend, perhaps you will try 2-3 days in getting the code. If you made a question on Monday, perhaps in the same day you can have the code.
All right. Last question from the attendees we have here. We have many questions, but the last one here is basically I'm reading here. As far as I recall, IAHR can simulate PRVs, but not include surge anticipating control valves.
Yes, they are included as well.
They
are included as well.
Recently included.
Yeah, absolutely. Are included. Wave anticipating valves.
Yes.
Wave included, sure.
All right, so good, it's been included. So 2 questions from the panelists. One is mine, and the other one is. Yes.
Well, you can send me an email particularly. I will send you my answer.
But my question is very rapid here. So do you consider? I know you mentioned that you consider cavitation in IAHR. You also consider distributed cavitation in IAHR as well. So it's not complete point, but distributed cavitation as well. Right?
We simulate cavitation with the most simplest model. The piston model is the model that we use, and well, but for me that is not important because I never recommend in practice that you project a system with cavitation or with depression. So we will advise you. We advise you that you have some parts of the pipe with depression. So what you need to do is push protect it in order to avoid that. But the model that we are using for cavitation, yes, it's included, and we simulate the piston model that you know perfectly. But it's quite difficult to assume that you have a cross section between air and between the water column is breaking by the piston. I don't believe so. But well, everybody models that.
It's a simplification, I know. And the last question is this: is a public domain software IAHR And the question is what the future of Alievi would be, because it really depends on the authors, the sponsors,
Well,
the continuation of this. How do you
yeah,
guys?
that is a good question. Alievi is not a public domain. It's it's our question. It's our software. So we give license and they can use for free. What is that? Because, well, we prefer to have the control. They can use, they don't have any problem. I wonder which is the future. I don't know. Perhaps if somebody want to buy it, that is a possibility that some people have asked. Well, I don't know about that. I don't know the future, but I'm sure that if that happens, we will advise at least within 1 year of time to prevent them that in 1 year, we will stop the use of friendly use and the for free use.
All right.
Now it's a free but not public domain, so you cannot download the calculus, the software, the program itself.
Mhm. Well, I think we are done with our questions. We had many. Again, thank you for fielding them all, and I think we had a good, very lively discussion between the attendees, panelists, and you, Dr. Cabrera. Really great having you in our. And again, we appreciate you sharing your thoughts, your experience in these applications related to transient flows and specifically to the software Alievi. Now, I'm going to ask here, we are going to have our next presentation here. It's going to be 10 minutes, Sylvia, or how should we proceed
We have
now?
time for a brief coffee break.
So at what time are we coming back? 15 minutes?
Minutes, yes, 15 minutes.
Okay, so we are all having some chance of catching up with coffee, and in 15 minutes we'll all be back.
Well, goodbye. Thank you for all your questions.
Thank you.
I'm happy with so many questions. That means that people has been attending my talk.
Yep, they did. Thank you so much.
Thank you very much. And usually it's a very friendly and very good software package, for sure. It's from Brazil as well, like you.
I remember Dr. Kelly.
Yeah? You know
Yep.
him personally?
Well, I was an undergraduate student. That was the last millennium.
Yeah. Okay. Bye.
Thank you
Bye,
again.
Sylvia.
All right, so I think we are at the end of our coffee break. It is great to see we all here back in our last speaker presentation today. We have here Trey Walters. We're great to have him here. Trey is a professional engineer and founder of the Applied Flow Technology. He's headquartered in Colorado Springs, Colorado. And AFT develops simulation software for various types of different transient flow systems, both in compressible flows, water hammers, slurry systems, and others. Trey Walter has managed a number of applications for turbo and fluid systems as consultant in various industrial applications. And this goes in different industries from power to oil and gas, municipal water, chemical applications, mining, and being himself a host and presenting several seminars across the world. The company he founded since 1993, so it's been on for several decades now at this point, and with 4 decades of experience in various aspects of transient and fluid systems. He has dozens of papers published, and he's an ASME fellow. And we are very happy to have him his presentation is titled Search Transient Modeling with AFT Impulse, Pipe Forces, Real-World Complexities, and Case Studies. Trey, is it great to have you here? Thank you for sharing your knowledge, sharing your perspective on transient with our group here. And the floor is yours. Thank you so much.
Thank you, Jose. And also thank you to Sylvia and David for all their organizing on the session this week, and for IAHR for hosting this interesting week of presentations. And it's also an honor to be included with so many esteemed experts in this field. And so what I want to talk about today, let me get my screen shared. There we go. The title is Surge Transient Modeling with AFT Impulse, Pipe Forces, Real-World Complexities, and Case Studies. So let me get my, excuse me, there we go. Let me get my video here organized a little bit better. So one of the things I was not really my purpose today was to go through all of the features and Impulse and just do a demo of the software. Instead, I wanted to focus a bit more on some applications and hopefully in certain areas, maybe actually teach some of the attendees some things in some areas maybe that they don't have experience in. And so with that, we will go ahead and we will dive in here. So what I'm going to start off with is an overview of Impulse, assumptions and capabilities. And this is and at this point, I'm not going to do any demos of the software. I'll just talk about it. We can do all of the standard transient modeling features, and I will talk about a couple specialty areas that we get into with Impulse. The second thing I'm going to talk about here is accurately predicting transient pipe forces. For a lot of the water industry, municipal water that deals with buried pipe, you don't care much about this because it's buried and there's very good structural support for the pipes, and the forces that happen because of the transients are just not a significant issue. When you are dealing with some of the above ground piping, this issue can be significant in the water industry and a lot of other industries as well. And so I'm going to spend some time talking about that. I want to also spend some time talking about complexity of real-world modeling. I'm going to talk about a liquid natural gas marine loading system that just when you take some of the very powerful methods and research that comes out of many decades of research by some of the specialists in academia, and then you try to bring that into something, a complicated facility with complicated transients. It's really quite, it's quite overwhelming, the types of things that people are trying to simulate and understand. So I'm going to talk about that just real briefly, the types of things people do in a liquid natural gas terminal. Certainly within the IAHR purview is the municipal water use is a big part of IAHR. And I'm going to talk about a case study of some transients in a municipal water pumping station. And then I'm going to go something kind of far away from municipal water to an alumina refinery, maybe about as far away as you can get on the spectrum of types of transients, and a catastrophic slurry pump failure in an alumina refinery. And I'll talk about that as that came about because of a water hammer transient. And then we'll draw some conclusions from there. So we will go ahead and dive in. So one of the claims to fame of AFT Impulse, it was first released in 1996. And I had, as Jose had mentioned in his introduction, I started AFT in 1993, and AFT Impulse was the third commercial software that was developed. And originally, when it was first written, I wrote about 99% of this. And now we have a big team of developers that work on it. I still work on it a little, but not as much as I did in the early days. But one of the things that's really kind of a claim to fame is, like, we saw demos of a lot of software. Some of it was in this week, commercial software, some that was more academic software, also the IAHR software. And you see these graphical model building tools. In 1996, this didn't exist for Microsoft Windows. At least I was not aware of it. If it existed, I never had heard of that. And so, to my knowledge, Impulse was the first simulation software for Windows that was graphical drag and drop in nature. So this is just a screenshot of what it looks like today. So that's one of the historical attributes of the software. And so we're talking, like 29 years ago. So when we talk about solution methodology, so AFT Impulse, there's two, okay? It has a built-in steady state solver, uses a Newton-Raphson method to solve steady state flow and pipe networks. And then that is used to initialize all of the transients, initial pressures and flows, so a transient solution can start from time zero. The transient solution method is performed with the method of characteristics, still kind of the most popular. It's not universal, but I think it remains the most popular method for doing surge modeling in pipe networks. Uses the fixed grid approach, all pretty conventional, the types of things that Impulse does from a solution methodology, stuff that has been in the literature for many decades. Some assumptions, these are pretty conventional assumptions that exist for the for doing this type of simulation is a one-dimensional flow. And so we've seen some good presentations this week of where, especially in hydropower, where that is not a very good assumption. And so there's been some interesting presentations made on some coupling between three-dimensional modeling. But in Impulse, we're doing everything with 1D. So all flow is fully developed at all locations at all times. We'll consider all flow fully developed even during the transient events. 2D and 3D hydraulic effects do exist inside of components, equipment, etc. And those are represented through things like curve fits, valve CV, K factors, other types of data that brings in outside information about the behavior of that particular type of equipment. And that is represented then in the software. Pipe friction for Newtonian fluids, it's treated, there's different ways to treat it, but certainly as a constant pipe friction, that's a very conventional assumption that goes back to the early days of the method of characteristics. We can also do variable friction and also frequency dependent friction. We use Brunel method for that. One of the other areas that AFT is a specialist in is in non-Newtonian fluids. And so I'll talk a little bit more about that in a few pages. And there's different kinds of non-Newtonian fluids. I'll expand on that just a little bit. But we support non-Newtonian fluids. And so when you have non-Newtonian fluids, and your pipe friction, of course, varies because it becomes not just a function of Reynolds number, it becomes a function of other types of things going on in each pipe. Pipes are 100% liquid full, again, a conventional assumption. And then also conventionally, we have some exceptions where transient cavitation occurs, which allows vapor to form, air valve inflow and outflow. But certainly when airflow comes in, then we can have pockets of air to handle things like air valves, et cetera. And then some features around empty pipe section features and sloped pipes where you can actually have computational sections that are empty of liquid, and that can be handled within a certain range of use. Other fairly conventional assumptions: constant thermophysical properties in each pipe. They can vary from pipe to pipe, so you can do temperature variations, but each pipe remains constant through the simulation. Constant temperature on each pipe through the simulation, but again, like I said, temperature can vary along with all the physical properties, density, viscosity, et cetera. Wave speed can vary from pipe to pipe. Each pipe has constant wave speed. During the simulation, wave speed varies pipe to pipe, but in each pipe, it's constant and it stays constant. So there's a assumption that any vapor that's formed or dissolved gases that come out of a solution, they do not change the wave speed. That's typically a conservative assumption. And conventional, just because of all the uncertainties that come into this type of analysis. Pipe system is rigid and doesn't move. Fluid structure interaction is ignored. Transient cavitation, when that is modeled, I'll talk about that in a moment. But all vapor, conventional assumptions here as well. All vapor exists at computing nodes. Vapor exists at mathematical points, does not displace fluid. So even though the vapor has volume, we do have some limited models for the vapor to displace liquid, but unless you use those limited models within a certain assumption range, the vapor does not displace the liquid fluid. And so it exists at mathematical points. Vapor bubbles don't move. And there's a single vapor pressure for each pipe. It can change pipe to pipe, but each pipe has a single vapor pressure, which is certainly a great assumption for when you're just doing water, because there's one vapor pressure for the temperature and pressure conditions. But when you get a fluid that is a mixture, when you talk about something like liquid natural gas, that I'll talk about a little bit later, and it is a combination of different hydrocarbons, cryogenic hydrocarbons, then there's different vapor pressure lines. And that's not accounted for. That's just, we're accounting for only a single vapor pressure, which is usually the minimum component in the fluid. Some capabilities I talked about earlier: drag and drop graphical interface. That was part of the software in 1996. Like I said, that was we were really the first into this area in Windows, doing things drag and drop graphically. And then over the next decade or two, then other software started to evolve their own graphical interface. We have extensive graphing features: double axis graphs, stacked graphs, animation of different profiles, pressure, example, pressure HGL, but you can really animate anything that you want. There's different ways to do animation. One of the things that I will talk about with some focus here today is calculating transient forces in pipes. And so for above ground piping, and engineers who need to make sure that piping does not move or break because of the transient forces, getting those forces accurately is really important. And so I'll talk about how do you do that in general mathematically, and then I'll talk about how Impulse does it. Non-Newtonian fluid modeling. So there's really kind of comes in two varieties. One is homogeneous non-Newtonian fluids. We have, I think, 4 different non-Newtonian models. One of the common ones that you see in the water industry is Bingham plastic, especially in wastewater modeling and sludge. And then we also can model heterogeneous non-Newtonian fluids, where, and that would be called like a settling slurry, where the solid particles behave somewhat independently from the fluid, and it has to be handled separately because it's really a heterogeneous fluid. And that's one of our areas of specialty, is a settling slurry. Certainly an important area in mining. Dredging is another area where this is important, and it comes up in a lot of different areas of industry. As far as I know, Impulse is the only software that does surge modeling for heterogeneous settling slurry modeling. I think it's the only software, at least commercially available. And I might be wrong on that, but I don't understand anybody else being able to do that. So when engineers and industry encounter that challenge, then they come to us because I think we're the only ones with really a solution for them. For transient cavitation modeling, we do the two most common transient cavitation models, which is a discrete gas cavity model, which has some thermodynamics built in, discrete vapor cavity model. I think we're all aware of the limitations of these models. And they just are what they are. They're about as good as have been able to be produced. There are some other more specialty models, but we can do that in a distributed cavitation mode. So this could happen anywhere in the system at any time. Vapor can form and collapse. So something else that we're well known for is how we handle scenario management. I'm going to show you this in just a moment, what this looks like. But we keep all the model variants in a single file with parameter linkage among generations and inheritance, okay? And so we've been doing scenario management in our software for about 25 years. I think we introduced it in the year 2000 into our software. So it's a very heavily used and proven out capability that we have. Another specialty area we've gotten into is modeling PATs. Another area, since we get into a lot of, and I'm trying to think, I'm sure this comes up in municipal water in certain areas, but it's definitely true if you get into things that are more like offshore. People are dealing with pipelines that go, for example, submerged going through rivers and lakes and things like that. It's variable ambient pressure with elevation. So rather than just have a single ambient pressure, you can actually vary the ambient pressure in your system. So that allows you, it doesn't change anything on the hydraulic calculations, but when an engineer often is interested is what's the gauge pressure in the system. And you can't really get an accurate gauge pressure if you don't know the outside ambient, or if it's changing, like you have a vertical pipe that is submerged in a lake or in the ocean. And so you're going to have a different gauge pressure all the way from the top to the bottom of that pipe. So, so we allow you to be able to put that in. Another very, very niche area for us is varying the G level with time. And if you say, why would anybody want to do it? I'll tell you here in a moment. It was actually one of my very first introductions to WaterHammer when I worked in industry. And as part of my introduction, I think Jose talked about today, but I started my career in aerospace. And we cared about G level changing from 0 or from 1, standard 1, and also how it changes with time. So I got involved in doing WaterHammer simulation where we had to introduce G level with time. And that was something I was introduced to as a very young engineer. So Impulse can model systems not at 1G, can model 0G systems. And in order to do 0G systems, if you look at some of the fundamental equations, if you formulate them conventionally, as you see in a lot of textbooks, in terms of head and volumetric flow rate, you'll see that there's a G parameter in those equations, and it's divided by G. So when you get a 0G, and that's, for example, if you're doing something in a satellite or space station or something like that, something that's orbiting around the Earth, then those software, if they can even do varying G, they can't do 0G. So all of the formulation done with Impulse is done with pressure and mass flow rate. So we've converted all of the fundamental equations, which you commonly see, like I said, in terms of head and volumetric flow rate, we convert them into pressure and mass flow rate. So, and that allows us to do a lot of different things easier, and it allows us to do 0G systems. And then finally, G level changes with time. And it's like, why is your G level going to change with time? Well, if you have some sort of a moving pipe system, and this would be like an aerospace vehicle, it could also be something like in a pipe system that you're trying to simulate what happens in an automobile that's moving. And that movement can change, can accelerate or decelerate. And it can happen quickly. If it happens slowly, then the G level changes with time are going to be negligible. But when it happens really quickly, in the terms of like say half a second or 1 second or faster, this can be really important in trying to understand what's happening inside your pipe system. So Impulse can handle that. We also have support for metric, all the metric units, and all the customary English units used primarily in North America. You can use either or both. You can use mixed units. I'll show you some examples today that we use mixed units. And so we can do all that. Okay, and then I want to just show you real quick what it means to have like a scenario manager, what it looks like in our software. So this is a model that was done by one of our customers about 10 years ago. This is a condenser cooling water system for a power plant. This happens to be a power plant in New Jersey in the Northeast United States. And my purpose here is not really to show you the model per se, but I'll just really quick go over it with you. In a condenser cooling water system, you have the heat exchanger where you're condensing the steam coming out of the turbine on the opposite side of the condenser. So they have a couple of condensers here running in parallel. They have their pumps are going to be high volume vertical turbine pumps. And then they have cooling towers down here at the bottom. And the cooling towers then, except for some makeup water, recirculate water back to the cooling tower basin here, and it recirculates around like that. Okay, that's not the purpose. What I wanted to show you here. Over here on the right is what we on what we call a quick access panel. On the quick access panel, you can see Scenario Manager. So this particular engineer at an engineering firm who did this project, you can see they have all of their different scenarios all within the same model. So these are not different files. There's one file, one Impulse file. This particular case I'm showing you right now is a case where both of these two pumps trip. And then after they trip, the signal goes to these two discharge valves and they close. That's typically going to be 45 to 90 seconds in a power plant. They've also got scenarios when they start up two pumps. They've got scenarios where they have one of the pump trips, but the other one's running. They've got different types of things that they've looked at with different vacuum breaker valves. And vacuum breaker valves show up in the power industry when you're wanting to protect condensers, expensive condenser equipment. So they've got vacuum breaker air inlet valves around the condenser to protect it when it has low pressures. There's typically around the pump discharges as well, more for pump startup. And so there's about 40 scenarios in here. I've seen some of our customers, the biggest I've seen is about 400, and they have 400 different modeling cases they looked up all in one model file. It's all logically connected. So that's something that we've been doing for 25 years. It's something we're well known for, and that's kind of just a bit of how it works, okay? We'll move on from here. Also, what people want to know often is how do I get data in and out? And so certainly it has native model building that you can build all your models from zero in the software, but you can also do, if you're one of the other tools that we have, commercial tools, is called AFT Fathom. It's a steady state modeling tool. So it's very common for our customers to have a Fathom model, and they say, hey, we're going to do a transient model with that. So you can bring that in directly into the Impulse software with all of the scenarios and all the fluid properties and everything, not the transient data, of course, but all of the configuration of piping. So if you do that, you've got like 95% of your information already done. So you can do your transient model. It's not as simple as just putting in the transients and running. I think we're all aware there's been some discussion of that earlier in the week about steady state models and choices made there and bringing them into transient solvers and some of the challenges there. But we have some tools to help assist engineers with that. Now, that's just bringing things in from one of our other software products. And then we also have robust automated Excel importing and exporting of data and graphs. So you can import data automatically, have an automated setup in a side Excel file, and you can import it and you can export the numerical data and also graphs and graph the numerical data behind the graphs, the XY data. You can get that in and out of Excel very easily. Third-party file formats are supported for piping network import and export. So we support import and exports of EPA-NET files. I'm always interested when I talk with, and I've heard it this week, a lot of the other software that were discussed talk about support for EPA-NET. The EPA, for those of you who don't know, it's a government agency in the United States called the Environmental Protection Agency. And so this was written as some sort of a public domain software 20 years ago or something like that. So it's still available. To my knowledge, not that many people use it, But what has happened over the last couple decades is the file format has become a bit of a standard format, especially in the water industry, for importing and exporting piping data. And so, but in the United States, when I talk to people, they'll call it EPA net. But when I'm talking to people outside the United States and they're not really familiar with the EPA is, and I heard people call it this week, it's fine, EPANet. And so it's always a little bit humorous because it's really comes from this government agency, United States EPA. But that is what it is. But that exists, and we can import and export it. And then we can also import from a Caesar2 neutral file, which is a pipe stress software. Another common file format is something called the piping component file, PCF file. We can import those, and we can also import GIS shapefiles. And I'm going to talk about this a bit when we get into doing the transients and forces and transient forces. But a lot of engineers, when they have done a surge model and water hammer model with Impulse or maybe other software, what they want to do is they want to translate all of that hydraulic information, which they're using certainly to make sure that the system is going to perform in a safe way hydraulically. But they also want to make sure it's going to perform in a safe way structurally. So they want to get the forces that happen within the piping, they want to get that exported into some pipe stress software, okay? And so we have 4 direct file formats that we support. And we can directly export a Caesar2 file, a ROR2 file, AutoPipe file, or Triflex file. So if you're anybody in your company and they have a mechanical groups and they're working on pipe stress for above ground piping, and they're using these software, we can export it. They can go in on the menu and say import from Impulse, AFT Impulse, and you can bring that in, okay? Then if they're not using one of these 4 industry leading software, then you indirectly can get the data into pipe stress software by just exporting it out of Excel, and you can do that. And you can import that in any pipe stress software that you want. Okay, so that's the overview. Let's talk about accurately predicting transient pipe forces. Okay, so why are transient forces important? Okay, so fluid transients, they cause transient forces. It's just what happens. Is the transients that are traveling at, as we all know, very fast, acoustic speed, 1,000 meters per second is common. They cause imbalanced forces, and I'm going to talk to you today in depth about why that happens and how to calculate it, okay? These transient forces can be really large. 10,000 pounds, 10 pounds force, 50 kilonewtons, and sometimes quite a bit higher, 5 or 10 times higher. You'll see applications where that happens. That is a lot of force that's happening, large diameter pipes. And if you haven't designed your piping support, now again, if the piping is buried, then you don't really worry about it, because as long as you have good support from the ground, is how the ground support and how the piping is buried, then the ground becomes the support. But when you have above ground piping, this can be a big issue. And somebody has to make sure that piping doesn't move around. If you don't account for that, something is going to break either quickly, suddenly, or over time with fatigue. And this happens over and over every day with a different operation. Something can just break eventually. Now, the worst case is that the piping breaks, obviously, and then you've got a liquid leak. If it's just water, then that can be dangerous, certainly if it's in an enclosed space. And there's certainly been unfortunate stories of water leaks that came from water hammer that was in an enclosed space, and because the water filled up, there have been people who have unfortunately died because they've gotten trapped in an enclosed space from water leaks and enclosed piping. But if you're dealing with something that is more dangerous and not as environmentally friendly, and maybe that is something that is flammable, caustic, just not environmentally friendly. Some cases, nuclear, radioactive materials, and you definitely don't want those to leak, right? So you care about the piping leaking. What you also care about is if this happens over time, your structural supports can break. And so you'll see this in a lot of, you go into facilities and you see where the piping supports are, and they're supposed to be supporting the piping, but they're broken, because this has happened. What I'm talking about today has happened over and over. And either suddenly they broke the supports on a very bad event on a single day, or over time they've weakened and eventually just by fatigue failure to support something, okay? So if you want to have a safe pipe system, you need to accurately assess what these transient fluid forces are. Okay, so in order to do that, you really need a complete force balance of what the configuration for the piping. So I'm going to focus on a particular type of force balance that happens between, we call it elbow pair. So it's along a piping run where there's 90-degree change in direction. That's a very common one that people care about in industry, okay? And so if you do a complete force balance, then if you do over time, and this is just a graph that comes out, I'm going to show you this example here shortly in Impulse, and we'll put some force assessments into it, and I'll show you how those are generated. But before I do that, I'm going to show you how to calculate them. And it's not as simple as a lot of people think. So this over here is showing the force in newtons. This is showing the force in pounds force over here. Now, one of the things that you can see is if you ever see a graph like this, and someone says, here's the transient forces that I calculated, okay? If they're not doing a complete force balance, then what happens a lot is that the graph doesn't start the force at zero. At time zero, it's something non-zero. And that really can't be the case, because if there's a force in steady state, then that's going to cause an acceleration. You know, so as long as the piping is not moving, then there's no really net forces. All the forces are adding up to zero. And so there cannot be a net force at time zero. And when you see one of these that's given to you by somebody else and it's not zero, at time zero, it's not a zero force, then you know that they haven't included all of the contributing terms to this. So I'm going to talk to you about how to do that. Another thing what you'll see is after the transient happens, the transient dies out, and then that should go back to a zero again. It should start at zero and end at zero. And if it doesn't do either of those, then the situation that you're in is they haven't accounted for all the terms, and things are missing, and you might not have an accurate assessment of the forces, okay? So why do they happen? They happen to due to fluid transient imbalances, for example, pressure in the pipes, which accelerate the fluid. I just said this right here, and I'll just make a note here, and I have one slide on this later. Other piping configurations that are not like elbow to elbow, okay, that they have something else than that, then they can have non-zero forces at time zero, and that's how the system exists. It has to be supported, but in steady state, there are forces happening. And that's really unlike when you have a pipe that's a discharge pipe, and it's some sort of like a vertical discharge pipe, and maybe it angles at the top through a valve, and there has to be support for that, and that'll be non-zero at time zero, and is true. That is for that configuration. But if it's an elbow, 90-degree elbows, it's going to be zero at time zero. So what happens that causes these forces? Okay, so let's talk about a piping system where flow is coming from left to right at a velocity v. It's liquid. The same thing happens in gases, steam. We're going to focus on liquids today. And so since it's liquid and the density for like a steady state is going to be constant, then we got a constant velocity going through, and it's discharging somewhere here at the right, okay? What we're going to pay attention to here is this particular point between these two elbows. We'll call it leg 1, 2. Now, a complete analysis is also going to look over here on the left from this elbow down to here in the Z or Z direction. And on this one over here, there'd be 3 different forces that have to be supported, okay? But to make this simple, we're just going to talk about this particular leg right here from 1 to 2, and we're going to ignore everything else for the time being. Here's our coordinate system. X is in the direction directly horizontal. Vertical direction is Z or Z. Okay, so we've got steady flow. Velocity equals V steady state. Pressure is nearly uniform. The friction is minimal. And then pressure is really the same everywhere. Okay, there's no net forces in the X direction. Okay. And so if you draw a graph over time of what's happening, and you draw a graph of what's happening, the force over time, it's going to be zero in this particular case, along this leg 1 to 2. Now we're going to look at is what happens when any transient event happens, okay? So somebody downstream of this to the right closes a valve, okay? So to make this simple, we'll just say it's an instant valve closure. There's one single transient wave, which is traveling through the system at a wave speed or a celerity A, and it's traveling in the opposite direction of the velocity. Velocity is going to the right, the wave speed A is going to the left, and we're going to look at a point in time where that wave is right here. Okay, so this part of the system over on the right is under high pressure for all the reasons we all know about water hammer. Is there's a pressure wave, and if this valve closed instantly, this is really like a Joukowsky pressure here. Okay, and so the pressure now at point 2 over here has gone from pressure steady state value up to the Joukowsky pressure. It's increased. Okay. And there's a net force. This interesting thing is to the right. So kind of intuitively, what a lot of engineers think is if there's a wave traveling from right to left, it's going to push the piping to the left. But that's not what happens. When the wave is traveling to the left, the pressure is high on the right. And so there's a force here on the right, which is greater on the right than the left. And so the force is pushing to the right, which is the positive X direction. So the directions are important here. Is it a positive or negative X force? This is going to be a positive X because the pressure is higher here and the force is greater here. A lot of approximations just take the Joukowsky pressure, they take the 2 pressures times the area, and they calculate the force that way. That is dangerous, and I'm going to talk about why. But it often is approximately true. It's not bad in some cases, but it's very bad in other cases. But we're gonna say that's approximately true in this case. All right. And so what happens if you look at the force over time in this leg 1 to 2 in the positive X direction? If this Joukowsky wave is a single wave, instantaneous, the force is going to go up also instantaneously to some maximum value that's approximated by the difference between the Joukowsky pressure and the steady state pressure times the area, cross-sectional area, okay? And then finally what happens is when the wave has traveled all the way over here to the left, the entire pipe system has gone to high pressure. Eventually there'll be reflections, but we're not talking about that right now. We're going to talk about just this first one, okay? And so what happens now is the flow is stopped by the valve. All of the velocity everywhere is 0. All of the pressures are at Joukowsky pressure. And so now when that happens, we're back to having equal pressures along the pipe. The force goes back to 0. And we're left with this like square wave that happens. And that happens very quickly and can be very high. And then the question is, what happens to the piping in here? Now, if there's no pipe supports or minimal, or the pipe supports are not holding something rigidly in place, this piping is going to move back and forth, and the forces are going to be taken by these elbows down here, and ultimately the piping, the straight piping that runs down here, that's where the load is going to be taken. And there's going to be pressure forces and fatigue happening and torque happening on these elbows. And if this happens every day, multiple times, there could eventually be problems in this whole moving pipe system. Something can eventually break at a flange, and there could be, an accident. Doesn't happen all at once, okay? So that's what happens. So let's look. And you know what? I have to apologize. I forgot to, when I started my my sharing of the video, I forgot to do it with sound. So I'm gonna restart my screen sharing and come straight back here. So excuse me, I'm gonna restart this, and then I'm gonna start again. My screen share. Start it with sound. You always have to remember to do that, right? Oh, okay. I think I have it with sound. Okay. We'll share it again. Okay. So you should be able to hear this. And so what I'm going to show you first is a video that I think almost all of us have seen before. I'm going to show you a slice of it. But then what I want to do is I'm going to slow it down and show you what happens much more slowly. So the first one, and the second one here, I'll turn off the sound because it doesn't sound right because it's going at 25% normal speed. So the sound is very not correct. But so let me go ahead and start this first one, and we'll just watch it through. Okay, so I think a lot of us are aware, if we've been in practicing in the field of pressure transients we've seen this. This is a video. It was in the year 2000 taken in Germany. And some of you probably who've been around for a while know some of the people involved with making this. But what I want to do next is I want to show you this in slow motion, okay? And then I'm going to turn off the sound. Oops. Stop. Let me make sure the sound is off on this one, because it can sound strange. Okay. So this is the same thing we just watched, but it's just when the pressure wave is coming. Okay, so we'll play this and you'll watch what happens in slow motion. Now there's a reflection that comes back, and the pipe's going to move the opposite direction. Okay, so from this, and we look, I think that's the end of it on here. Yeah, that's the end. So if we come back and we look at this chart right here that I just showed you, what I showed you is that the pipe moves in the direction of where the transient started. If it's a high pressure transient, it's a low pressure transient, then it's going to be the opposite. This will be a low pressure area. But if it's a high pressure transient, it's going to move to the right. Okay, so we're going to be able to look in slow motion and be able to determine where did the transient come from? Was the transient starting from this pipe in the top and was the valve in this leg and the transient's coming from here? Or was it over here on the right coming from here? And the way to see that is, which way does it move on the first time you see the transient? And then you'll see the reflection where the wave goes through and it reflects, and then it moves the opposite direction. So watch real carefully. Which way does it move on the first transient? And if you look at there, you can see it moves to the right. And the next transient, it's going to move to the left. Okay. So what that means is that whatever is causing, if this is a high pressure, like there's a valve closing, it happened over here on the right. It came through, it traveled around and exited over here. There was a high pressure on this elbow, which made the entire assembly move to the right. Then it hit a reflection point, a reservoir or something over here on the left. It reflected back. When it came back, then this became the high pressure area over here, and this became the lower pressure area, and then it moved to the right. Okay, so how do you calculate all this stuff? Whoops. Get back to my presentation here. Okay, so how do you calculate the transient forces? So really, all the fundamental parameters needed to calculate the transient forces can be obtained from the water hammer simulation results. What that means is you can get all of this by every single parameter you need. When you do a water hammer simulation and you have all of your pressures and flows and other information at each one of the computational stations, all of that is what you need. And if you add it together properly, then you can predict what the forces are going to be in the pipe runs, okay? And you have to include all the contributors. Let's talk about how you do that, okay? So, so we're going to start first talking about an elbow pair. And in our case here, let me see, I have to pay attention to time. I've been going on here, looks like for about 40 minutes here. Okay, good timing. And then I'm finishing 20. Okay, so all of the fundamental principles in order to calculate these forces are simple and well known. They're just our conservation of mass momentum. And certainly if you've done the transient simulation, then within the approximations of the computational software, you use Impulse or whatever else is being used, then these are being calculated and honored, aside from things that are neglected, but primarily the important terms are being accounted for. But we have to pull those terms together and add them up, okay? And so if you take our good old representation of Isaac Newton's second law, and you apply it to what's going on, we're going to talk here about a case that we've got an elbow coming into a pipe with a valve, and then there is a diameter change, and then there's another elbow down here, okay? And so if you look at all of the transient forces that are happening, there's a lot of other forces happening. There's gravity and things like that. We're going to treat that as some sort of other steady state forces. What are the transients that are causing the pipe to move? And these are all the ones that cause it to move, okay? You've got over here on the left, you've got a momentum change in the x direction. So again, here's our coordinate system. X is positive to the right. Z is positive to the vertically. We've got a pressure force here acting on this assembly of pipes. And this assembly of pipes, if there's no rigid supports in here, it moves as a unified collection of components rigidly connected. It moves back and forth, okay? Unless there's a support that holds it, okay? And that's what you need to have to keep it from moving, okay? And the question is, how strong does that support need to be in order to support this, okay? So there's going to be a reaction that we want to know that is going in the positive x direction. So there's a pressure force here acting really ultimately on physically on the elbow, on the inside diameter of the elbow in here. There's a change in momentum in the x direction we need to account for. There is a frictional force happening in the pipe. As we come into this valve, there's a momentum change across the valve, that is due mostly because of the change in diameter. There's also pressure forces on the upstream and downstream side acting on the valve, more friction forces, and then downstream in this elbow, same thing as the upstream elbow. We got pressure forces acting on this elbow, and we got momentum change here in the x direction. Okay, we got to add all this together. Okay, so Newton says this is the representation of what's happening, the forces, which is the net force we want to calculate. What's that net force? And F equals ma, and here's the ma part. And it's kind of nasty looking when you look at it there's the control volume part, and there's also what's happening on the flux terms, control surface part. How do we apply this? So let's go ahead and talk about it, okay? So there's two ways to do it, okay? The first, and both of them give equal results, and they completely account for everything except for some assumptions I'll make that are typically negligible, okay? So here we are. We're going to take Newton's second law. F equals ma. And so we're going to look, and we're going to say this one, in this case, this component reaction method, we're going to get the forces acting on each one of these 5 components. Now, obviously, this can be it could be any configuration. There could be more pipes, valves, orifices, all kinds of things can exist inside here, okay? So we're just talking about this configuration, but what I'm talking about today can in principle be done on any configuration where there's elbow pair, okay? So we're going to get them all, okay? So let's talk about the components in the piping. We're going to talk about the pipes first, then we'll talk about what I'll call the junctions components, okay? So let's focus on the pipe. So we're going to look at this pipe right here. And it's got a outside diameter, inside diameter with fluid in the middle. Okay, so this is the looking at it along the cross-sectional area, and this is looking at from the outside, what you see. And then we have a sliced view looking at the pipe. Okay, so what we're going to do is we're going to draw control volume. Control volume is going to go if in this view here, it's only going to get the pipe material. Okay, not any fluid at all, and we're only talking about the pipe. You do a control volume around the pipe material is what we're going to do. This results in a cylindrical annulus for the control volume. And since the control volume doesn't go around any fluid, then we don't have to account for any changes in the fluid here. We're only accounting for forces on the pipe solid material. Okay. So the transient force experienced in the x direction by this control volume is the friction. That's the only thing the pipe is experiencing as the friction on the inner pipe wall. But it's a little bit more complicated than steady state friction because we have transients in that pipe. Different pipe computational sections can have velocity, as we all know, in different directions. It can have every single computational station can have a very different velocity. Depends what's going on, right? So what you have to do is you have to go to every single computational station. You have to get the mass flow rate in that station. You have to get the resistance term, where there's a frictional term that comes in. You have to add them all up along the pipe and then multiply by the area of what this is acting on, okay? And And so, and then you have to do this every single time step. This has to be updated because the friction factor changes. Unless you're, and the mass flow rate certainly changes. The friction factor can change or not depending on what you're modeling, but the mass flow rate is going to change. So every computational station, every time step, you add these up and you get the frictional force acting on this particular pipe. Now let's talk about the other pipe, the other pipe here, the second pipe is done the same way as this one, okay? Let's talk about what happens on these junction components. We're going to first talk about we're going to say the fluid volume inside these junctions is really negligible relative to the volume of fluid in the pipes, okay? So we don't really have to account for the fluid mass inertia in here contributing to the forces. Okay, and so really the description of the forces on these elements are really the same as their steady state behavior. So we're going to draw a control diagram around each junction and determine the force components in the x direction. Okay, so we'll start off with the first elbow here. And that one's just going to be easy. It's going to be the pressure force acting on the area, projected area going in the x direction, and then the mass flow rate at location 1 right here coming in, and times the velocity. Okay, the valve is slightly more complicated, that we have the pressure forces acting and then the change of momentum across that valve, mass flow and velocity. Okay, and that goes from 2 to 3. And then of course the final one over here at 0.4, it's really the same as the element 1, but it's going in the opposite direction. So we have to add those together. So if we add them all together, what really happens is, by the nature of how we've drawn our control volume, is that this term drops out because we've drawn a control volume in a way that we don't have to account for any of these contributions here. But we do have contributions that happen across the control surface, okay? So one, we have the inlet bend happening up here. Then we have what's happening on the straight pipe section right here. We have what happens across the valve. We have what happens in the other pipe. And then we have the final valve, okay? And these are all the pipes, all the contributors. And if you add them all together, then you get a complete representation of what are the forces acting along this kind of, we consider rigid assembly, how it happens over time, okay? So I'm gonna encourage you to be careful with this assumption that has happened. Engineers, being very practical for many decades, have made this assumption. I'm going to show you some of the pitfalls on this assumption. I'm going to call it the endpoint method, where what the assumption is the pressure forces acting at the end of the assembly, P times A loads, are the ones that dominate. Often this is approximately true. It's not always, and it can be very incorrect. So people who do this endpoint method, which has been done, this has been done for many, many decades. And this one, often it's true. So it's not like you're always getting incorrect results, but there are times it's not correct and sometimes it's very incorrect, okay? So what happens is essentially they're ignoring all of these terms. All this is ignored, and the only thing that we're accounting for, we're representing the forces here by these terms right here, everything else neglected, okay? And I'll show you what the implications are if you do that, okay? Now, there's another method, there's another way to get the forces in this assembly, okay? And we're going to draw a different control volume, okay? So rather than draw a control volume around the annulus area of the pipe material, we're going to draw it around the outside of the entire piping, okay? We're not encountering any fluid at all, except for the fluid right here and here, but that's in the Z direction, which, since we're only adding up things in the X direction right now, that doesn't matter, okay? So, so really all of these flux terms drop out, and the only thing that matters is this second term right here, okay? And we ignore the mass of the fluids inside the junctions, same as component reaction method, as being much less than the pipes. And so how do you add this up? How do you solve this? Well, if you go through the process of solving this for a pipe, you end up with something like this. This is the discretized, after you go through the calculus and you discretize it, it's really what we would call the acceleration accumulation method, okay? It's the change in the acceleration of each fluid station inside the piping, and you add all those pieces, those changes of acceleration up, and you actually get a representation from Newton's method of what's happening in the pipe forces. And then you can do the same thing on the one down here. And so the interesting thing is this looks very different from what I showed you on the previous page. It gives the exact same results because it's all doing Newton's method. If you draw the right control volumes and add up the pieces directly, you'll get the same results. This method here is actually a lot easier than all the stuff that I showed you before. This one will also work for very well for compressible transients and also two-phase transients if you want to. So, and this method was actually developed by one of my colleagues at AFT, Scott Lang. And we wrote an ASME paper on it in 2022, I think it was. And I'll make some reference to that later. But anyway, show you how that works. Okay. So how does this play out in a system? Okay. Well, I'll show you in a moment answering that question. But let's talk about a point force. So there's a whole bunch of other configurations. So what I've been talking about so far is two elbows, 90-degree elbows. You can have non-90 elbows, obviously. You can also have an elbow going out through a discharge valve, and there's discharging, okay? So in this case, you have and even in a steady state, there's a force of the discharging pressure going out through here. There's a force acting. And you can also have, like, for example, an elbow. You want to get a force going along this whole assembly. You've got the forces going on here, similar to before, but now you've got the momentum loss going out through this nozzle out here. So you can add this all up as well. So there's different types of configurations where you can do this. It's all the same thing of adding up the pieces correctly, okay? So let's do an example here, and I'll show you this in Impulse real quickly. So this is a system where we've got a higher pressure tank. It's atmospheric tank flowing down through a system here out to a lower head tank. And the flow is going through by gravity to make it simple. There's a filter here. We might care about what the force is here between J2 and J4. Also along this run right here across this valve. This valve we're going to close in 2 seconds, but we're not going to close it all the way. We're going to take it from 100% open to 10% open. Okay, so we're going to throttle it down, but not completely down to here. Okay, and then you can see some of the pipe runs in here. So over here, this particular pipe run is 20 feet, 6 meters. Diameter is 20 inch, about 500 millimeters. Okay, in here, and then all of the piping is all the same diameter. It's 20 inch, 500 millimeter pipe. Length is 20 feet, 6 meters, 20 feet, 6 meters. This is a longer run. What you find out on these longer runs, the forces can be just bigger because there's more time and there's more friction, there's more things going on. So this pipe run right here is 480 feet or 146 meters up to the valve. And then this one is 40 feet, 12 meters here, okay? And so you can get forces in this particular leg right here, also here. I'm going to show you both, okay? And then I'm going to show you an Impulse how to actually calculate these, okay? So if you go in on and do the forces right here, and the coordinate system would be whatever coordinate system that you want. I mean, this could be the X direction, this could be the Z or Z direction. You can put those coordinate system into Impulse, and it'll tell you the forces in the direction that you care about. But this would be the force right now going in the positive direction of flow, which is going to be pushing downwards, okay? And we've got time down here on the bottom. We've got pounds force on the left. We got kilonewtons over here on the right. And you can see the force goes up to about 1,000 pounds, 4.5 kilonewtons. Happens a little bit after 2 seconds. Okay, so that's what happens there. This is a little bit bigger force that happens in this run. You can see the force comes up, and the peak happens not when the valve stops moving at 2 seconds, but delayed by about half a second. It's about 9,500 pounds force. About 40 kilonewtons happens along this run right here. That's a pretty big force, and that's going to be pushing right now in the direction from left to right is where it's going to push out this way. So we need some structural support to push back, or else it's going to move. Okay. So I'm going to show you what this looks like in Impulse. Okay. So this is the model in Impulse. And so you can do, Impulse does a drag and drop, but ultimately it's a 2D representation like a flow chart. You can do a flow chart in X, Y, or you can do it in isometric. So right now, this particular model, you can see this grid is an isometric grid. So that's how this model has been built. I'm going to turn off the grid because it's kind of a little bit distracting right here. So here's our model. Okay, this particular reservoir right here, it's 50 feet high, 15 meters, and down here it's 3 meters, 10 feet. Okay, we got flow going through here. So the question is, or what are the forces in here? So I want to get those forces. So what I'm going to do, so I'm going to put this up here. I'm going to come in and I'm going to, and so even though it's true that all of the method of characteristics calculations has all of our data, if you don't add the piece, keep track of all the pieces properly, then you're not going to have it. You've done your computational run with, and you say, oh, what I want to get the forces. Oh, I didn't keep the data that I need. I didn't save it. So if you want to make sure you've saved all the data, you need to say where the data is saved. So we're going to go ahead and do that right now. We're going to come in here and we're going to add in some forces here. I'm going to call this one J2 to J4. So this is what we call the J2 branch or elbow. This will be another elbow here. So this run right here, it's going to start at pipe 2 and it's going to go to the end of this pipe 3. So the starting pipe is pipe 2. It's the inlet, and the ending one is pipe 3, and it's the outlet. And this right now is shown in feet. I can also make this be in meters. And so I can put it here in meters, and this, if I did that, this would be 6 meters, etc., which is the end of this pipe. So you can do it either way. So I'm going to do this one in feet. I'll show you all the results in kilonewtons, okay? So this goes out here to the end of this pipe, which is 20 feet, about 6 meters, okay? We're going to do another one here that goes from this J4 out here to J6. And that goes from pipe, this is pipe 4, so it goes from the beginning of pipe 4, the inlet at 0, and then it's all the way to the end of pipe 5, which is at 40 feet down here. So I'll say it's at pipe 5, 40 feet. I can come in and I can put in, if I want to, some XYZ coordinate systems. So that makes it easier when you want to take these forces and you want to map them very easily into pipe stress software. If you define your coordinate system here, which direction these forces are, you can just import them directly into your pipe stress software, and it'll have the coordinates and the force coordinates all in the proper direction. Okay, so we're not going to worry about that right now. So I'm going to say, okay, I'll save this. I'll run this model. We can come in here and one of the things we'll just show about impulse. I didn't do a big demo, but you can. One of the nice things is we can show parameters as many times as you want in as many units that you want. So this one shows the flow rate in cubic meters an hour is 2,400 cubic meters an hour through the system. Velocity is 3.5 meters a second, or 11.5 feet per second, 10,000 GPM. The maximum pressure in each pipe, 35 PSI absolute or bar absolute, 2.5, okay, 2.4. So you can have parameters as many times as many you want. You can mix and match metric units. You can put in cubic meters an hour. You can have another column of liters per hour, liters per second. So that's one of the flexible things that we have. But right now, that's not what we care about. We're going to focus on the forces right now. So if I go over here and look at the forces, it's going to take my 2 force sets. I called it, this was the name I gave to them. It's going to tell me the maximum absolute value, because the forces could go positive or negative. This is the maximum. We can look at the maximum in the negative direction as well. But right now, we're going to focus, what's the maximum force, positive or negative? So in the first one, the maximum is 1 pound force, which is 4.8 kilonewtons. Okay, and then in the second one, it's 9,700 pounds force, 43 kilonewtons. Okay, so what does that look like in terms of graph over here? So I'm going to come in here and I'll look at the first one here. This is I'm going to come down. And I'm going to generate this graph right here. So this is the graph I just showed you, okay? This is now for the for this one right here. This is the one that we're talking about right here. And this one that goes up here, again, you can see this in kilonewtons and pounds over here, okay? And then I can go and I can look at the other one, which is going right through here. We're calling that J4 to J6. And then we can generate that force as well. And this one is quite a bit larger. I'm coming from here to here. And so I will expand this back out. And you can see this one is almost 10,000 pounds, or like 45 kilonewtons is the peak that happens right here, okay? So if you had a young engineer And I'm going to go back here to my PowerPoint. You had a young engineer who said, hey, all that matters is the pressure force at the beginning and the pressure force at the end. And they said, oh, I've got that pressure. I got the pressure predicted in my water hammer simulation. I'm just going to print it out into Excel and I'm going to do the math. Pressure at 1, pressure at 4. And they're going to add these up. This is what it looks like. This is what I just showed you. If you include all of the terms in Newton's second law, if you only include the endpoint pressures, you actually get a force. First of all, it's not 0 at time 0. It's like minus 1,000 pounds, about minus almost 10 kilonewtons at time 0. And it's bigger than the actual force. It's in the wrong direction. It's in 14,000 pounds, which is 60 kilonewtons, but it's going in the reverse direction. And they would get the wrong magnitude of the force in the wrong direction. And they might design pipe supports around that. And they could have a failure ultimately. So you want to account for all the things in there, okay? So that is kind of it on pipe forces. And so now I want to talk about I like showing this because it's really interesting. Ultimately, you have to see, I'm doing on time here. I'm finishing in about 10 minutes here, right? Okay, so let me go ahead and let me speed up here. Okay, so this is just the types of complexities you could end up in. This is a liquid natural gas system. There's 6 pumps pumping from 2 tanks. And it is a shore-to-ship loading system that's pumping natural gas onto a ship. And then there's these perk valves that are by requirement have to close in 30 seconds on the ship. And there's the transient happens, 25 transient events all happen at the same time. 6 pumps trip, 6 valves have to open in 10 seconds, 13 valves have to close in 45 seconds. There's 6 check valves that slam. And some engineer has to figure out what are all the pressures in here and what are all the forces that happen. Okay, let me pick up and go ahead to this municipal water pumping station. This is an application of a municipal water pumping station that was done by one of our customers in Barcelona, Spain. So it's in the, those of you who are familiar with Barcelona, like David, this is a Tibidabo pumping station. These are elevations and meters. It's a pumping station that actually serves an observatory up in near Tibidabo, the Fabre Observatory, and some houses, and there's some storage tanks, okay? The goal of the project was the station had exceeded its design life. They wanted to replace mechanical, electrical, and the equipment. They wanted increased capacity in the pumps. I think it was 20 or 30% more flow, okay? Secondary goals is they wanted to gather field data on the check valves, and the check valves slammed. And they wanted to determine if an accurate model was possible to inform the utility. Could they develop a model that worked to predict this? So in the future, they could just use simulation to do this, okay? So engineering was performed by a company called Aquatech, which is a branch of Suez, the Barcelona office. You can see the piping, the overall piping that goes through the whole system was 1.4 kilometers of piping and 300 millimeter piping, 12-inch piping. They had 2 pumps in the pumping station. One was an operating pump. There was a backup pump. You can see the flows here let's see, flows of 0.08 cubic meters a second at 155 meters, 220 kilowatts. Here's it is in English units, 2,900 RPM. They had surge vessels on the upstream side and the downstream side of the pumping station. So what it looks like inside the pumping station, the 2 pumps that were replaced, they have surge vessels outside. Over here on the right, I had a chance, fortune to come visit this pumping station. This particular pump right here, you can see there's pump 1 and pump 2. These are the 2 pumps. They were axial flow pumps. Here's the 2 surge vessels that existed outside the pumping station right in here. These were the check valves. They had normally before this project, they had swing check valves on both locations. But part of this project, what they did is they put a nozzle check valve over here. They tripped the pump and they measured the pressure to see what happened with the swing check and nozzle check. They measured it. They had the conventional pressure transducer this was down here from the pumps where the 2 pumps came together. is where they had the measurement, the conventional measurement. Then they had a high frequency pressure transducer that was measuring pressure down here. And this line, this was the 300 millimeter line. The two lines coming out of the pumps were the check valves were both in 200 millimeter lines. This is the model that was developed with the pumping station. These were the two pumps, check valves, surge vessels, etc., going all the way up to the different locations around Tibidabo. These are the pressure spikes that were measured. The blue one is with the swing check valve, and this is pressure in meters of head. And this is the nozzle check valve. So you can see the red one, it was much less. It's actually over 80% reduced with that nozzle check valve. Same transient. This is what when they compared it to an impulse model on the swing check. The blue was the swing check data, and the gray was the predicted with the transient model. And then with the nozzle check valve, you can see the orange was what they measured, and then the gray was what was measured there. They also compared the model predictions to the levels inside the surge vessels, and so that's the gray was what was measured. I'm sorry, the blue was measured for swing valve, and the orange for the nozzle check valve. And the predictions in gray. This is a chart, much that was shown by Professor Cabrera. And if you just want to take these valves and you want to compare them to what the conventional characteristic data is, let me see, I'm trying to check my time. Oh, I think I got my time off. I have 20 more minutes. I got a little bit confused there, so excuse me for my timing. I was off in my time. Okay, 20 more minutes. So, so the swing check valve, the data that was measured. So, okay, so let me go ahead and Professor Cabrera talked about this type of chart, check valve chart, quite a bit. And I have some interesting things to say about it. But this is something that those of us who've practiced for very long have seen a chart like this. It's based on measured data. We have two different tests that were done, that were combined here in this one. This data right here it shows the maximum reverse velocity that happened when the check valve actually closed. That is the one that causes really the slam, the spike, okay? Then over on the x-axis is the deceleration of the fluid in meters per second squared. And then over on the right, I got it chopped off here. We have a chart, it doesn't show it here, excuse me, that has this in English units, but this is the one with metric. So this is where the swing check operated, and this is where the nozzle check operated. Now the interesting thing that you can see right here, the swing check, is that this isn't close to any of the other data that has been measured before, okay? The comparison, you have to be careful with this, and I'd caution what Professor Cabrera was showing in the previous slide is each of these were done for different diameters. And so this is this particular data from Thorley was for a DN 100 millimeter or 4-inch moving ball valve. The swing check valve here by Thorley was for a 100 millimeters, and then Ballon has it for 200 millimeters, 8-inch valve right here. That's the green one down here. It's not as much data as Thorley had, and it followed it fairly well, but you have to be careful because the data is not the same. When you take this data with the velocity and acceleration, it's not the same with the diameter changes. So really the data that we all have as engineers to work with, if it's dimensional, that it exists in 100 millimeter, 200 millimeter, and 300 millimeter, and that's it. You'll also see this chart in dimensionless form. And that's a little bit more tricky because it needs more data, but it does exist and it can be used. Okay, we have to be tricky. But the interesting thing here, like I said, is this 200 millimeter 8-inch check valve. That should line up with what was going here with Ballon's data for a swing check valve, this green data. And you can see it's very far away from that. One of my colleagues at AFT wrote a paper on this. This was just, I think it was last year. It was an ASME paper, and they really went back and looked at all the raw data behind these curves. There is so much scatter around these curves. A lot of us like to take these curves and just use them. Be careful doing that. There's a lot of scatter. And if you're interested in reading about that, there's this ASME paper, a review of check valves in a steady flow behavior analysis and design, done by one of my colleagues, Scott Lang. And it talks about how much scatter is around this and how much you really should be thinking as a practical engineer and trying to solve practical problems. Be careful just using this data with a curve fit because there's so much scatter around it. Okay. ultimately what happened is Aquatech Suez, the utility in Barcelona, said, well, let's go ahead and use nozzle check valves. One of the interesting things when they did this test, because they had the original swing check valve was installed down here. This one they put a nozzle check, but the original swing was in here. When they did the test, they assumed that the surge vessels would be enough to kind of protect the pump station. And this goes back to one of the presentations on Monday. I think Brian Singh mentioned that a lot of times utilities don't want you doing tests on their operating systems, right? Well, in this case, the utility said, fine, do a test. And they slammed closed, well, they turned off this pump manually. This pump was off, so there was no flow going on this one, on this side. They turned off this pump manually and they just measured what happened. And that happened downstream as I showed you here. And they measured what happened on inside this nozzle check valve. And what happened is they were inside the pumping station and made such a noise it scared them terribly. But the pipe supports that were supporting this pump down here got bent. It actually did some structural, so there are supports down here to support some of these forces I was talking about that happens. They have pipe supports in here to support them, but they weren't quite strong enough and it bent the supports. And so, so they had to fix that after they did the test. But when they did the nozzle valve over here, it was much more gentle, no problem with the supports, okay? Ultimately, excuse me, they replaced both of the swing check valves with these nozzle valves because they were just more gentle. And that was what the utility did. I think they were thinking about whenever they did pump station upgrades in the future, just to go with nozzle check valves. They're more expensive than swing check valves, not as common. Swing checks are so common, but they're much more well behaved for water hammer. And you'll see that in this chart down here, the swing check valves for 100 millimeter and then 200 millimeter are down here. And what this means is for a given deceleration of the fluid as it's backwards flowing through the valve, the like you have, like, say, this 4 meters per second squared, you get a much higher reverse velocity when the valve closes, which means it's a much higher valve slam effect, pressure spec. And that's what we saw in the data at the TB pump station. Now, they had data down here on nozzle valves. And so, and you can see it's much, much lower, which means that that reverse velocity is a much lower reverse velocity. That's why you don't get the high pressure spike with nozzle valve. So this red one is it's actually a 300 millimeter nozzle valve. There's another nozzle valve in here, down here. And then did Ballin, the only nozzle valve data we have is from Thoroughly. Ballin didn't test any nozzle valves, it looks like. So, okay. So what are some conclusions that can be drawn from this study that was done by the engineers at Suez Aquatech in Barcelona on their local pumping station? Okay. One is nozzle check valve significantly reduced pressure surge from check valve slam. In Tibidabo station's case, it was over 80% reduction on the pressure surge. And then they were able to pretty well predict the simulation of the pressure transients that happened in the system. And so they confirmed that, hey, you could develop models in the future and we could, predict what's going to happen ahead of time without having to test. And so this whole project was published at a conference in 2018. Pressure surges 2013. I have some references at the very end, and if you get a copy of this, it tells you where to find this paper. Surge transients due to check valve slam. So you can go read about the full detail from the conference paper. Okay, let's talk about something very far away from municipal water, which is alumina processing and alumina pumping. This is also very far away from Barcelona and in Jamaica in the Caribbean. So on the morning of April 6, 2016, an alumina refinery in Jamaica had a catastrophic failure. A manual pump discharge valve stem broke, which caused the valve disc to slam closed. Immediately after that, the pump casing exploded. Hot caustic slurry sprayed onto nearby personnel and equipment. One technician was seriously injured. He survived, but he was seriously injured as a result of this. He got sprayed on this very hot caustic fluid. Okay, so this is a picture of the refinery in Clarendon, Jamaica. So what's an alumina refinery? What is it? Okay, it's a refinery which processes raw bauxite. Raw bauxite, this is like a bauxite mine. It turns out that Jamaica happens to be a small island in the Caribbean, has some of the best bauxite formations in the world. And so they mine it there in Jamaica, and then they also process it, okay? And so this was at the Jamalco refinery there in Jamaica where this is all processed, okay? So you get this raw bauxite. You can see it's red, okay? If you've ever been into an aluminum refinery, and I have, everything is red because of this bauxite. I'll show you some pictures here in a moment, okay? I've never been to the Jamalco refinery. One of my colleagues at AFT has, but I've been to one of their refineries in South America, okay? So through a complicated multi-step process, alumina, not aluminum, or as our British friends would call aluminium, and North America, we tend to call it aluminum, or aluminium, same thing, okay? But that's not what's done here at this point. It's called alumina. It's aluminum oxide. Two aluminum molecules and 3 oxygen molecules, aluminum oxide, also shortened to alumina. They make this, and they get this alumina out of the raw bauxite. After they do this, and they get the alumina, this is typically shipped to another facility, which is a smelter, which uses the alumina to form final aluminum or aluminium type products. But this is not aluminum, aluminium, this is alumina, okay? So how do you do this? This is actually a very complicated process, and I understand it probably more than the average engineer, but I'm not an expert at all in it. But they take this raw bauxite, just in summary form, they take this raw bauxite, it comes in on trucks or by trains or sometimes by ship, okay? And they feed it into a process, they mix it and they crush it, and they mix it in with lime, they put in steam, they have these digester units. Then they go off into these blow-off tanks, which then have some recirculating process that comes back out. Some of the blown off steam recirculates back into the process. Oh yeah, here's the caustic soda that comes in, and it goes through this whole process. I won't talk about the whole thing, but this is ultimately you feed in alumina, or you feed in bauxite from the beginning, and by adding in caustic soda, and going through these different separators, digesters, heat added, steam, etc., you end up with alumina out here, which then is formed. It's like a dusty compound of a silver dusty, kind of like aluminium, but it's not. The silvery dusty compound, which can then be smelted. Okay, so this accident happened right here in these blow-off tanks. Is where the accident happened in 2016. And so if we take a blow up on that, it's a multi-stage process, okay? And so this was the final digester blow-off tank. And where the accident happened was right here. There were some pumps that took the, at this point, it's a very hot caustic fluid that's being pumped, and it's getting pumped, and it's going out to what we call a sand trap out here. And that sand trap collects it and processes, and then it goes on through the rest of the whole facility. And there's a pump in here called the number 3 DBO pump, digester blow-off pump, that failed, okay? So that's the big picture. That's narrowed down in on this one part of this big process, okay? This is the pump that failed. So just if you want to see the system, they had 2 pumps. There's the number 3 pump and number 4 pump. And there was also a number 1 and number 2 pump we're not going to talk about. That didn't have any problems on this day, okay? And then they had 2 tanks that they called the DBO tank number 1, number 2. And so both tanks supplied both of these pumps, and they had these discharge valves, which are manual, okay? Here's the only pressure measurement they had. It was not high frequency. It took data, I think, every 15 seconds or every 1 minute or something like this. It was not helpful from water hammer at all. And you can see some of the pipe run lengths over here. The longest one is really out here. This was the pressure transmitter that came out to the sand trap. And so that one was like 100 meters long. But everything else was pretty short. It was like little runs of 3 to 7 meters as you kind of come through here. 9 to 23 feet of different pipe runs as you come through here. Okay, the fluid properties was a caustic slurry density 1.26. So it was caustic, it was chemically dangerous. It was also dangerous thermally because it was at 110 C. But near boiling point because they would drop the temperature pressure, and that was kind of how the process worked. So it was near the boiling point, and they would do some pressure drop off. And that was how they did part of the separation process, okay? So it was near atmospheric pressure at the pump suction, near atmospheric pressure and this temperature. And at the pump discharge, it was like 4 bar discharge pressure. I can't remember what that is in PSI, maybe like 75 PSI. The whole thing was rated for about 100 PSI, 7 bars. That was the maximum it was rated for, okay? So let's go through and see what happened. So 2 pumps serve the 2 tanks, 1 run at a time every morning. And this is when the event happened, in the morning when they would cycle between pumps 3 and 4. This is what happened over 8 months. With number 4 pump running, they'd start pump number 3, and they'd start a process of opening and closing these valves and closing the pump, okay? So that happened at 6:29 a.m. They do this every morning. They'd switch to pump 4. The next morning, they switch to pump 3, back and forth, okay? I'm going to go through some of the steps here. Okay, so on this morning, on January 16th, pump 3 was off and this valve was closed right here and it was not running. And so the flow was going through the purple line, coming from both tanks, going through this pump, through this discharge valve, with this process. Everything was working fine, 6:29 a.m. And so then what happened, that was prior, at 6:29 a.m., they started the daily switchover process. So the first thing they did is they opened up this valve. It was a manual process that was not easy. It was like a manual, it was a big valve. And so they opened the valve, but there's no flow yet. I'm sorry, I take this back. They turned on the pump, but this valve was not open yet. That's the next step. They turn on the pump, but there's no flow because the valve is closed. Pump is operating, it's a closed valve for a few minutes. This valve pump over here is still running, okay? Then what happened at 6:31 a.m., they came over here to manually open this valve, okay? This is a laborious manual process. It takes some time. So now they've got flow going through the red line and the purple line, okay? Going out to the sand trap. And then they came over and they closed off the valve on the other side at 6:33 a.m. A couple minutes later. They closed this valve, again, a laborious process. That stopped the flow through this pump. They hadn't had a chance to turn off the pump, this number 4 pump, when the accident happened, but that would have been the next step if they hadn't had the accident. What happened at 6:37 a.m. is this discharge valve broke. It slammed closed, and then that sent a pressure wave back towards this pump, and the casing failed catastrophically. So I'll show you what that looks like in here. So this is the everything is red, like I showed you in an alumina process. So, but I'll focus here on where the accident happened. We've got the number 3 pump over here, number 4 pump. It pumped from here and into here, and it went out the top. The broken valve, this valve right here broke. This is what happened. It snapped. This whole valve stem snapped, and this valve seat, it moved real quickly, and it caused a water hammer to go back against the pump. What happened to the pump, here's the motor for the pump. The pump is located back here behind this wall. You can't see it on this image. So if you go back and take a picture of the pump back here, this is what happened to the pump. It's a pretty big pump, maybe almost 2 meters in height, 6 feet. And it blew this open. And this is where the fluid came out and sprayed onto people and equipment. Okay, they took the pump out. This is where it took it out, and you can see for scale, this is a sawhorse right here. So this is maybe 1.5 meters tall to 2 meters tall pump. This is where the pump casing blew off. Here's another image of it up close. You can see inside. This is where this was all material. This is the pump impeller inside here, and then the inside of here is all the volute where the fluid is captured. Another picture right here. This is the piece that blew off. Okay, it's a pretty big piece. I'm not sure, almost 1 meter in size, maybe 0.5 meter to 1 meter in size that blew off. Okay, this is a model that was developed of the system. We don't have any measurements here. The only measurement we had was right here at this pressure measurement. And so we know what it was during the steady state. And so that was used as a boundary condition. It was feeding through 2 tanks through this pump. This valve was the transient that failed. And so we don't know how fast it closed. We're not even sure if it closed 100% of the way. It might have felt, it just was enough. Okay, so if we assume that it closed instantly, we get a pressure here. This is PSI on the left. This is time in milliseconds. This is bars over here on the right. Okay, and you can see there's a pressure surge here of almost 100 bars. up to about 1400 PSI. The rating on the pump was 100 PSI and 7 bars. That was the rating. So that is what would have happened if it happened instantly. If that valve closed over 10 milliseconds when it broke, then the pressure would have been more like about 80 bars. But it was appreciably much more than 7 bars or 100 PSI. And this is what happened with the flows, okay? So contributing factors to the failure, and then I can wrap up on time, is one is the pump casing. It was, and I'm not an expert on this, but one of my co-authors we wrote a paper on this is a material expert. It had 28% chrome iron, ASTM 532 class 3 type A. Okay, so what that meant was it's better at handling abrasive solid particles that existed like in this aluminum refinery. But that's the advantage. The disadvantage, it's more subject to brittle failure, which is what happened this morning. It had a history of casing cracks and leaks. 6 times in the previous 5 years, they had to, among the 4 digester blow-off pumps, the casing cracked and had to be replaced. They just replaced it, okay? The discharge valve, the number 3 discharge valve had broken 3 times previously, and they welded it back together. This time it broke, and unfortunately, when it broke, it cracked the casing. These happened to come together. Every morning and every day, there was a cycling from cold to hot because there was thermal cycling on the pump casing in the entire line. So that was a contributing factor. So in conclusion, valve slam after mechanical failure can cause catastrophic system failures. In general, more attention should be paid to system design where valves can slam closed after mechanical failure. A lot of time engineers say, oh, our valve is going to close over half a second, 1 second, 5 seconds, 10 seconds, no problem. Except when it fails and it closes instantly. What's going to happen to your system? More attention should be paid to this and unexpected excessive pressures from component failures, especially when personnel safety is involved or there's a dangerous fluid, which is flammable or something else, thermally dangerous. Require at minimum a Joukowsky equation. Should we design for that? That's a question for the engineering community. I don't know the answer, but there are failures that happen when this happens, okay? So there was a whole paper written on this for Pressure Shortages Conference in 2023 that I authored this one, so you can read about that as well. Just in general, for conclusions today, Impulse has been used worldwide to model surge transients in municipal industrial systems for 30 years, 29 years. It has a rich feature set, excels at predicting transient forces and pipes. Case studies presented show successful applications of municipal water pump station in Spain, alumina processing slurry pumping system in Jamaica. Here's some references if you want to go read about some of the papers behind this. And now I'm ready for questions. My apologies, I'm 2 minutes late. I think Sylvia is going to help us here.
Great, thanks a lot for this wonderful, excellent presentation. Even if the session is really long, I'm sure that all the participants participate with a lot of fun with your videos and with the examples, practical example that you show us. I really appreciate your focus on assumption of AFT impulse that you explain very well, step by step. And I also appreciate the strong focus on industrial applications. We can now pass to the first, I think, very interesting question. Can the assumption G-level changes with time be used to model earthquake-induced transients?
Okay, I'm trying to read this and see.
Yeah, in the box, in the chat in the bottom. So if the model, if the AFT impulse can model earthquake-induced transients.
Okay. Usually I can see why can't I see the questions? Here, I'm going to stop sharing. Can you stop the sharing?
Yes, you can stop the sharing.
Then I can read it and make sure I'm answering it correctly. I can see questions from the.
There is a chat of question and answers on the bottom of your Zoom.
Well,
maybe if you stop.
I was seeing them. Okay, I'm sorry. Can you ask it again? What the variable G? What do they want to know about that?
If the question is related to the possibility of modeling transients induced by earthquake.
Gosh, I can't understand. Can you, I'm able to see the webinar chat. Can you post it in there for me? It'll be used to model earthquake-induced transients. Now I understand. Okay. I say yes and no. Okay. So right now, the capability is G level in one direction only. I think earthquake transients has, if you ignore the vertical G level and you say only lateral G levels, you could do that, but it's only in one direction. Okay. So yes and no with the limitation.
So another question is related to the correlation between movement and the direction of the pressure wave. When the pressure wave returns to the two elbows, it comes as a negative wave from opposite direction.
Yeah.
Does it not make movement in the same direction as the first positive wave?
Yeah.
Always get two movement in pairs in each direction.
Yeah, that's the question. Yes. So it can, depending on the configuration of the piping system, you can have forces in both directions, a positive wave and a negative wave. So if you let it go on long enough and how it reflects, it's all very, obviously we all know it's a complicated piping system. So you can, so it's one of the challenges for engineers who do pipe stress is that they have to do supports that support both positive and negative movement sometimes in the system.
Okay, so there is another question related to the fluid structure interaction. If I understood well, the structure behavior in FT impulse is considered as a rigid solid. It's a two-way dynamic interaction between the fluid and the structure, or a one-way interaction from the fluid to the structure?
Yeah, so I think it's conventional in method of characteristics. We don't have as good an understanding on fluid structure interaction, maybe in the university to be able to simulate that, but in commercial application, the understanding and the coupling is usually not very good. So the assumption is, which is usually conservative, is to neglect fluid structure interaction and the pipelines don't move. And really they shouldn't move. If you have good supports, they shouldn't move.
The problem
they
is
do in your lab sometimes, you say in your lab.
Additionally, is this software capable of simulating pipeline anchoring?
So no, that's really, you need to get into the pipe stress software, and the most popular ones, the most commercially popular things like Caesar 2, Roar 2 is quite popular in Europe, Autopipe, etc. And they do that, and so we transfer data into those software, and they can do a proper job of understanding what's happening structurally with the anchoring. But that's not what Impulse does. Impulse is doing the hydraulics only.
Okay, so we have a final question because you explained that you use the Newton-Raphson method to simulate steady state conditions. And did you experience any convergence problem?
Yeah, so those of us who've worked with method of characteristics, one of the nice things is that it's all explicit. So you're not dealing with convergence. It's explicit calculations each time step. And so convergence is just typically, it's not an issue. So the answer would be no.
Okay.
That's other issues emerge numerically, but not convergence.
And again, if I understand well, you do not simulate viscoelasticity, just elastic pipes.
Well, elasticity comes in through the waves. There's waves, the elasticity of the pipes and of the fluid contributes to the wave speed, but that's the conventional assumption of method of characteristics.
Reduce
Alievi software is the same. It's the same thing. Yes.
Yeah. Okay.
Yes.
Thank you.
All right. Thank you so much.
Thanks to you and thanks to all the participants. We will continue tomorrow at 1:30 Central European Time. So please check your time. We will have two very interesting presentations. The first one from Info Water Pro from Autodesk, and the other one from Lina Sela of University of Texas, Luke Singh of Xylem, and Gerard Riano of Cornell Tech. So see you tomorrow. Bye-bye.